All right, good morning again, guys. Welcome to the New Jamaica Foundation Csec Physics Marathon. Uh, yeah, really grateful that you guys could make it, and I do hope that today's session is going to be a success and that you guys will be able to learn some new things or better understand some concepts that you didn't understand before, right? So we already did a sound check, but just to confirm everyone is still hearing me, right? And are you seeing my screen? Is it in full
Yes,
screen?
sir.
All right, and I just changed the slide. You guys can see that, right?
Yes, sir.
All right, good. All right, so my name is Mari Brown. I'm going to be your tutor, moderator, facilitator for today's session. I do have a background in physics, but my focus area is really math. As you can see, I got a grade 1 Csec physics and both units. Okay. So I'm somewhat competent in my humble estimation, right? I studied actuarial science at the University of West Indies. So basically, I'm just a few years older than you guys, not that much of a difference. So I relate with you guys a bit. There's no need for formality. That's okay. So just to go through some preliminaries with you guys, communication is going to be key, particularly because while I'm sharing like this, I won't be able to read what is in the chat. So if it is that you have a question that you'd like to ask, you're going to have to open your mic and say it. I don't mind being stopped and asked a question, right? Slides will also be provided at the end, so you don't have to worry about writing everything that is on the screen, right? Occasionally, I'm going to need volunteers to read as well. I can't be talking for the entire duration of the session. I'm going to need a few seconds or minutes here or there to rest. Just want everyone to double check at this time that their cameras and mics are off at this time, right? Good. And I'm also going to need 2 volunteers to keep track of any errors that might be on the slide, whether it's grammatical or calculation errors. So I'm going to need 2 volunteers. So who would like to volunteer to assist me with that? Then just tell me your names and I'll make a note of it. Anyone? All right, then I guess we just have to move forward with that and hopefully that there are no errors. If there are, I'll try to remember and fix them at the end. And for those watching the recording, you guys can email any additional questions that weren't answered during the live session, right? So this is basically an outline of what our session this morning is going to look like. We're going to start off with paper 2, with 2022 paper. Then if we follow suit, we should have a lunch probably around 12:45, and then afterwards we'll do some paper ones, right? And before I get started with some quick examination tips, guys, please don't use a calculator that you're not familiar with. Different calculators, they have different syntax rules. And if you don't understand how to enter information into the calculator, it might give you a wrong answer because of how that calculator is programmed. So it's best to use a calculator that you're familiar with. Please prioritize areas that you're strong in. If you know you're not good on alternating and DC current magnetic induction, leave that question for last. do the moments, do the kinematics, do your heat, do anything else. Leave the questions that you're weak on for last. Answer, as I said, answer all questions on the topics that you're comfortable with before attempting any question or problem that you're not comfortable with, and avoid wasting time. There are 2 hours and 30 minutes for you to score 100 marks. So you have about 1 minute and 30 seconds per mark. And finally, CXC doesn't deduct marks for additional information or incorrect answers. And sometimes they even mark with carry-on error. So it's best for you to leave something on that paper. Don't leave it blank. All right, so now we're going to start with our Csec 2022 paper. Right. So this is the first question, and it says activity of a radioactive substance was measured over a 6-minute period. The results are recorded in the table. Got the table, then it said using the grid provided in figure 1 and figure 5, photograph the activity A versus time t and draw a smooth curve, right? Then it said to define the term half-life, right? Next, from the graph on page 5, calculate the average half-life for the radioactive substance. Then we're going to use that graph to determine how long it would take for the activity of the sample to be reduced to 10 disintegrations per minute from its original activity level. And finally, or at least for this part of the question, we're to define the term nuclear fission, right? So I'm a bit limited with what I can do on an online setting. I wouldn't be able to use exact graph that was on the paper, but I'm able to use like online software such as Desmos, which is a really good graphing software, to plot it for you and give you guys a sketch of what your graph should look like. And it is a good idea to read graph questions completely before creating the graph. Sometimes I ask you to determine values based on your graph. And if you make a graph too small, you're going to have to redo the graph so that you can get those values. It's a good idea to read and see if they ask you anything like determine the activity when, or determine the time when the activity is 10, right? Now, I have a question for you guys. What is my graph missing? Just a general question. You can go ahead and just unmute your mics and let me know what you think the graph is missing. What is it that you must include on your graphs to get full marks?
Title.
Title, yes.
Scale.
I heard someone else.
Sir, scale.
Yes, you need to have your scale. What else?
Axis labels.
Axis labels, good. Is there anything else that I'm missing? I think that's more or less it. If there's anything else that you guys think about that we're missing, you can just always leave it in the chat, somebody will see it. But yeah, always include your title, your scale, and your axis labels. Right. So going back to the question, the very first question asked us, what was the half-life, right? So half-life is the amount of time it takes for a radioactive substance to decay to half of its original mass or half of its original activity. So if the activity was 100, it's the time it takes to get to 50. If the activity was 50, it's the time it takes to get 25, right? The activity was 80, is the time it takes to get to 40. And then when well, based on our graph here, it says that when our disintegrations per minute was 10, the time was 4.394 minutes, which is the same as 4 minutes and 23.64 seconds into our experiment. I think the next question was to define nuclear fission, right? Nuclear fission is essentially just one big atom breaking apart into smaller, more stable pieces. And for completeness, you could add the fact that there is some sort of energy output that results from a decrease in mass. But all you just need to remember is that in fission, a large atom breaks into smaller, more stable atoms, right? Now we're going to determine the half-life of our sample. Now there's something that I should make known to you guys here. My graph right here, it cuts the y-axis at 85. That was my choice. Your graph, on the other hand, might actually cut it at 80, might cut it at a little bit lower. It's up to you because you're drawing a best fit curve. It doesn't necessarily have to go through all the points or start from 80. That choice is up to you as long as your best fit curve closely follows the trend in the points. For me, I believe that based on the trend in the graph, it would have cut the y-axis a little bit higher than 80, not necessarily anything. That's just my personal opinion. That's why my graph cut it right there, right? And so using my graph, I'm going to go ahead and calculate the half-life. So remember, half-life is the time it takes for the activity to decrease to half of its original value. So it's going to be the time when the activity was 42.5 less the time when the activity was 85, right? So that's going to be 1.42 minutes for my first half life, right? Now, with any experiment, there are going to be some sort of errors along the way. And it's probably best for you if you do this calculation more than one time. And then you average the results instead of just using one set of calculation, right? So we're going to do it again. And this time we're going to be using the time when the activity is 21.25 minus the time when the activity is 42.5. And you're just basically finding half of the activity and then reading from your graph. And so we get 1.424 minutes for this case. And I'm going to do it one final time when my activity is 10.675 and activity is 21.25. Half-life for that is 1.423 minutes, right? Now, it's recommended that you use an average of 3 half-lives for accuracy. Could use 2, but it's better when you use 3 for accuracy. Now I'm going to average those values. So it's going to be 1.423 minutes plus 1.424 minutes plus 1.423 minutes divided by 3. And that's going to give you 1.423 minutes for our average half-life. Now, before I continue, is there any questions that you guys have? Remember, I can't see what's in the chat. If you pose a question there, it's unlikely that I'll be able to see it based on how it is that I'm presenting at the moment. Any questions are good and we can continue. All right, take it that we're good. The next part of the question asks us to, let's see, the equation below is given. The equation below is an example of a nuclear fission reaction, right? So we're going to have uranium 290. What's that? I'm not sure what element that is. And then we're going to get 2 newtons in the atomic mass data for the nucleids given in table 2. Calculate the energy released in the reaction. State your answer in joules, right? So we know that our energy produced in this reaction, or the change in energy, is going to be equal to the change in mass multiplied by the speed of light squared. That equation is very famous. E is equal to mc squared, or more accurately stated, change in energy is equal to change in mass times c squared, or delta E is equal to delta mc squared, right? And so if we're going to find the change in something, we need to know what it was before and what it was after. So our initial mass is going to be the mass of uranium plus the mass of our neutron, and we're going to be using the values that are in our table, right? So uranium has a mass of 235.118 U atomic mass units, plus our neutron is 1.009 atomic mass units. So add that together and we get 236.127 U. The final mass is going to be the mass of all our products. So it's going to be the mass of K90 plus the mass of Ba144 plus 2 times the mass of a neutron. When we add all of those together, we get 235.746 atomic mass units. So our change in mass is going to be equal to 0.381 atomic mass units, right? Then we're going to start plugging in these values into our equation. So we have the change in mass, and we know that the speed of light is a constant, right? So that's going to be 3 times 10 to the 8 meters per second squared. And we have to convert that atomic mass unit to kilograms. So it's going to be 0.381 multiplied by 1.66 times 10 to the negative 27 kilograms. Put that into our calculator and we get 6.325 times 10 to the minus 28 kilograms. And when we square the speed of light, we get 9 times 10 to the 16 meter squared second squared, meter squared per second squared. Multiply those two numbers and we get 5.692 times 10 to the negative 11 joules, right? Now, changing mass, it's the same thing as mass loss or mass defect, right? So it's pretty much the same. Any questions here?
No, sir.
All right. As I said before, guys, the slides are going to be provided after our marathon, so you don't need to worry about writing down everything that comes up on the screen, or you don't need to rush to absorb it all. If you miss something that you don't see how I got the numbers, you can ask me to repeat, but you don't necessarily need to write it down right now. Right, now we're moving on to question 2 on this paper. Very first question, we're given a table and they want us to determine the physical quantities and the SI units that correlate to each other, right? So our derived SI unit, the very first one is meter squared. So what physical quantity is that? Go again, I didn't hear you. Area, that's correct. And then if a physical quantity is density or derived SI unit is?
Well, kilometer cube.
Go again. Let's repeat that for me.
So kilogram meter cube.
Kilogram per meter cube. Don't forget the per. Right? And then this one here, we have kilogram meter per second squared. Anyone wants to tell me what they think this one is? Right, so the answer is force, right? So that's going to be kilograms, which is our mass, and then meter per second squared is our acceleration. So that's going to give us force. And for velocity, we have meter per second squared, right? The next question asks us to state Newton's second law of motion. Anyone wants to go ahead and give us that law?
So the rate of change of momentum is proportional to the applied force.
Yeah, that is correct. You are correct. Another way to state that is pretty much what we've been using in physics right across the board is that force is equal to mass times acceleration, right? But if you want to give the exact wording of the law, then you definitely want to say the rate of change of momentum is proportional to the applied force, right? Thank you. The next question says, a basketball has a mass of 500 grams. Calculate its weight in newtons, right? So if you guys realize part C of the question is essentially building upon what you answered in part B, right? So there are some cases where if you look at the subsequent questions, they kind of give you an idea what should have come before, right? So you know that part C, you're going to have to use force is equal to mass times acceleration to do that calculation, right? So it's likely that they would have asked you to state that law before. It's unlikely that they would have asked you to state Newton's first law and then ask you to use Newton's second law in the subsequent question. Forget what I'm trying to say. So even if you didn't remember which one of Newton's laws was the second law, if once you saw that follow-up question, you would have gotten some sort of idea that it is the law where they have force is equal to mass times acceleration, or as they say, the rate of change of momentum, right? So we know that weight is a force, and it is the force of a mass when gravity is acting upon it, right? So 500 grams, it's the same as 0.5 kilograms, and we multiply that by 10 meters per second squared. Some cases they tell you to use 9.8, other cases they tell you to use 10 meters per second squared. In this case, I said we're to use 10, right? If it is that you're given the option, I'd recommend using 10. It makes the math a lot simpler. And so we end up getting 5 newtons as our answer. Next part of the question says that figure 2 is a scale drawing of a vector diagram representing a basketball's velocity, OA, and the wind's velocity, OB. Complete the scale diagram on figure 2 to determine the resultant velocity of the basketball. And so they've given us our diagram right here. Next part of the question asks us to determine the magnitude of the resultant force in meters per second and its direction in degrees from wind's velocity, right? Now, there are 2 ways that you can approach a question. You can use a triangle method or you can use a parallelogram method. In truth and in fact, they are one in the same. It's just up to you whether you feel more comfortable using one method or the other, right? But the 2 of them is going to give you the same answer. For me, again, I'm limited in this case. I don't actually have the physical paper in front of me. I'm using an image, and so my answers are going to be slightly different from yours in this case, right? So as I said, I'm going to use a parallelogram method. We start by adding in our lines, parallel lines to the forces that were given, right? Till we've completed our parallelogram. And then afterwards, we just connect point O to the other end of that parallelogram to get our resultant force, right there. Now I've added a second yellow line just for me to get the angle. So you'll be measuring the angle right here. And my answer is 13 degrees. That's from the direction of the wind, right? And if OB is 5 centimeters, then my resultant force is going to be 6.8 in terms of the length on the scale diagram. So your answers should have a similar angle and they should be in a similar ratio between OB and our resultant force. So if on your diagram you have 10 centimeters, then you know that your resultant force should be about 13.6 centimeters, give or take. If you have 2.5 centimeters as your OB, then your resultant vector is going to be half of that length. So you're looking at about 3.4 centimeters right there. Any questions are good? All right, so as I was saying before, the parallelogram method and the triangle method, they're practically the same. The only difference is that with the parallelogram method, you end up drawing 2 additional lines, right? So it's really just your preference as to which one you would want to use. If you're more comfortable with the triangle method, use the triangle method. If you're more comfortable with the parallelogram method, use the parallelogram method. Now we're at question 3. And this is just a simple question that asks us to complete the table comparing thermometers. So the very first row in our table says that the thermometer it's used to measure extremely high and rapidly changing temperatures. It has a range from about minus 200 degrees Celsius to 1500 degrees Celsius. That's a very wide range. And as it said, it's used to measure rapidly changing temperatures. So it's very likely that this kind of thermometer is going to be a thermocouple, right? The next row, they only give us the range. And
Yeah, that'll be clinical, that one.
yeah, this one is going to be clinical. And you know that it's clinical because of the small range, right? Clinical thermometers, they have a very narrow range. And the reason why it's narrow, it's because of its use. It's often used to measure changes in human body temperature. So when you go to the doctor, that's the kind of thermometer they'd use on you. They wouldn't need a thermometer that goes up to 1500 degrees Celsius because no human body temperature goes that high. It goes that high, then you're practically dead. And the last one is going to be our laboratory thermometer, right? And that is because the use of it rather, it tells us that it measures the boiling and freezing point of room temperature, boiling and freezing point of water and room temperature. So you know that you're going to have a range from about 0 degrees Celsius to 100 degrees Celsius if you want to measure that range. And as I said, it's going to be a laboratory thermometer. On the Celsius scale or ice point, or the point at which water freezes, is 0 degrees Celsius. And the Kelvin scale, that's going to be 273 Kelvin, right? Difference between the Celsius scale and the Kelvin scale is an additive constant, right? So you just add 273 to the Celsius value and you get the Kelvin scale. So it's just a shift of the Celsius scale, right? Next question says, the graph in figure 3 shows how the pressure P varies with the inverse volume 1 over V. State the law associated with this graph. Anyone wants to tell me which law this is?
Boyle's law.
Boyle's law, that's correct. All right. And do you mind me asking, what does Boyle's law say?
A constant temperature pressure is inversely proportional to volume.
That's correct. All right. So pressure is inversely proportional to volume. So that means you're going to get a curve, right? But if you realize for this graph here, you don't have a curve, you have a straight line. The reason for that is because they didn't plot pressure against volume. They plotted pressure against the inverse of volume, right? If you plot pressure against the inverse of volume, you're going to get a straight line graph. So that's why this graph is straight instead of being a curve, right? Next part of the question says that we're to use the graph on page 12, sorry, to determine the volume when the pressure is 250 kilopascals. So we're just going to look at the graph, find 250 kilopascals on the y-axis, trace it across until we meet our plotted line, which is slant, and then afterwards we're going to read down and get the value of IV. that corresponds to that, right? So when pressure is equal to 250 kilopascals, 1 over volume is equal to 0.19 centimeter cubed, right? And so 1 over V is equal to 0.19 centimeter cubed. If you want to find our volume, let's do a little bit of transposition here. So you're going to have 1 divided by 0.19 centimeters cubed, and we get our volume to be 5.263 centimeters cubed. Next part of the question asks us to use answer both to calculate the new volume when pressure is increased from 250 kilopascals to 975 kilopascals, right? Remember, from Boyle's law, pressure is equal to a constant over volume, so it's inversely related. And so when you multiply pressure and volume, it's going to give you a constant. So whatever pair of values that you multiply, you should always get the same constant. And because of this fact, we know that pressure 1 multiplied by volume 1 is equal to pressure 2 multiplied by volume 2, right? And so we need to find the volume when pressure changes to 975 kilopascals, right? And so it's not anything difficult, just a bit of transposition here. We're going to divide by 975 kilopascals to get our new volume. That's going to be 1.350 centimeters cubed. So if you realize there was an increase in pressure, and that leads to a decrease in volume, right? Now we're going to move on to question 4. I'll take silence as we have no questions at the moment. Right. So question 4 asks us to define the term pressure, and we're to state its SI unit. Now pressure is the force applied normally per unit area. SI unit is going to be Pascal or PA. Normally here just means perpendicular 90 degrees. That's all it means. So it's the surface area that you're applying the force to. All right. Next part of the question asks us to calculate the liquid pressure that a diver experiences at a depth of 0.5 kilograms below the surface of the sea, given that acceleration due to gravity is going to be G is equal to 10 newtons per kilogram, and the density of water is going to be 1025 kilograms per meter cube, right? So the pressure from the water, we know, is equal to rho GH, or density multiplied by gravity multiplied by the height of the water above the point, or you can say the depth of the point, right? Now, if we're going to calculate the total pressure acting upon the diver, we have to include atmospheric pressure, right here, right? The question does ask us to calculate the liquid pressure. I'm not 100% sure if we actually want the pressure due to the water or the liquid being above him, or they want the combined pressure of the water and the atmosphere, right? So I've done the calculation to show you the combined pressure right here. So all you're going to be doing is just adding atmosphere to that value, right? So we're just going to be plugging in values from our question and calculate it. So we got the density as 1,025 kilograms per meter cube. We know that gravity is 10 newtons per kilogram. The depth was 0.5 kilometers, which is pretty much the same as 500 meters, right? And from that depth, it's very likely that the diver is going to be in the sea. You're not going to find any kind of pools or anything like that in an enclosed space on land. And you know that whenever you're working with an open container, open body of water, you generally add atmospheric pressure here. That's one of the reasons why I'm still not sure if they just wanted the pressure due to the water alone, or they want us to give us the combined value. So what you could do is that you could calculate the pressure due to the water alone, and then afterwards add the atmospheric pressure to it, like a two-part calculation, if it is that you're unsure. And if they only want the value of the pressure due to the water, they'll just mark the first part and ignore the remainder. And if they actually want to combine, then they'll mark everything. So that's one way you can use to get around that situation of not being sure. And so multiply the numbers and then add in our atmosphere to get 5,226,300 pascals, or 5,226.3 kilopascals. Next, we're asked to state Archimedes' principle, and then it says a boat which has a weight of 800 Newton floats in seawater. If the density of the seawater is 1,025 kilogram per meter cubed, calculate the volume of the seawater displaced by the boat, right? So Archimedes' principle states that when completely or partially immersed in a fluid of the fluid being displaced, right? Now going a little bit further than Archimedes' principle, now, if it is that a body floats, we know that the weight of that object is equal to the up thrust being applied to it, right? So up thrust is always equal to the weight of the fluid being displaced, but only when the object is floating is that up thrust equal to the weight of the object. So that's a very important thing to note. So the weight of the boat is going to be equal to the weight of the displaced fluid. So we're given that the boat weighs 83,000 newtons, and we're to find the weight of the displaced fluid. Now we know that weight is a force, and that's going to be equal to our mass multiplied by our acceleration due to gravity, right? And so we know that the acceleration due to gravity, as I said, For simplicity, it's easier for you to use 10 instead of using 9.8, especially in cases where they don't specify which value to use 10. It makes the calculation a lot simpler. You're just dividing by 10 there to get 8,300 kilo, right? But the question didn't ask us to calculate the mass of the water being displaced. It asked us to calculate the volume of water
Yeah,
being displaced.
transpose.
Yeah, we're going to transpose, right? We have the density, we know the mass, so we can find the volume. So density is equal to our mass divided by our volume. Transpose to get volume is equal to mass divided by density. Now we just plug and chug, and we get 8.098 meters cubed. All right, good with that so far, right?
Yeah, it's
All right, thank you. Question 5 asks us to define the term longitudinal wave. Now, if you guys realize so far, we've done 4 questions. You've got a graph question, you've got a few calculations, and you have gotten a few questions that ask you to define something or state it or just to explain. So even it is that you're not good at doing calculations in physics, you can still pass the exam. There are a lot of questions out there that ask you to define something or state something. So you can still pass the exam even if you're not good at doing the calculations, right? You need the calculations to get a very good grade, but you can still do fairly well if you get all of those questions, those easy questions that ask you to state things, right? Maximize what you're good at, maximize what you know that you can do. Anybody can make a mistake when doing a calculation. Not everybody is going to always be able to remember the formulas and plug in the values. But if you master the definitions and stuff like that, you can get a good amount of marks from that. Right? Just don't forget any keywords and try to be as concise as possible. If it's a 2-mark question, you don't need a paragraph, maybe 2-3 lines at most. If it is that there's a formula associated with the definition, you can put the formula as well. Sometimes you can even use the formulas to define things, right? So if we ask you for velocity, don't just put V is equal to displacement over time, right? Instead, just say that velocity is a rate of change of displacement. You know that rate means time, so displacement divided by time, same thing. But to get back on track, this question has asked us to define the term longitudinal wave, right? So a longitudinal wave, in a longitudinal wave, the particles vibrate parallel to the direction that the wave travels. Typical example of that would be sound. So that means that if the wave is moving from left to right, the particles are also vibrating from left to right. So they're traveling, the particles vibrate in a parallel direction to the direction that the wave travels, right? Now, figure 4 is a wave train on which the points K to S and A to D are shown. And they want us to write 2 letters whose distance between them and the wave train represents the amplitude. So before that, anyone wants to define what amplitude is, and then someone else or the same person can define what wavelength is? All right, so amplitude is Anyone?
Would it be the highest point of the wave?
Yes, but I'd rather if you say it's the highest or maximum displacement from its rest position. It's a little bit more detailed than what you've said, but sometimes the devil is in the details and you have to be just a little bit more specific, right? The answer isn't wrong. You're right. So it is the maximum height. You just want to mention that it's from the rest position. And you want to give me 2 letters that represent or amplitude. You guys are answering in the chat, but I can't read the chat right now. You have to open your mic. Right.
LMP.
Sorry, I just got a little bit too fast here. But we do have a point saying that L would be the maximum displacement. What I actually wanted to do here, I wanted to give it as a pair, so 2 points, so meaning A to L, that actually represents your displacement or your amplitude. If you say L and P, they're going to assume that you mean the distance between those 2 points. It's like they want to give the endpoints to represent the amplitude. Get me? So it can be A and L, or B and N, C and P, or D and R, right? That's going to give you the displacement from the rest position. And then someone wants to define wavelength for us.
So here, like the distance between 2 successive crests or troughs.
Yes, right, that's correct. Wavelength is the distance between 2 successive crests, which would be our highest point, or troughs, which would be our lowest point. You can also say that it's the distance between 2 successive points in phase. And phase here just means that the particles are going in the same direction and that they have the same amplitude, right? So examples of wavelength here would be K to O, L to P, M to Q, N to R, or O to S, right? Last question on this page asks us to state 2 differences between light waves and sound waves. And
Sir,
again, as I said to you guys, sometimes, yeah, go ahead.
Like I said, light waves don't need a medium, but sound wave needs a medium.
Yeah,
Someday.
correct.
And light wave can travel in a vacuum while sound wave cannot.
That is correct.
And
However,
where is that, sir?
continue what you're saying and then I'll just comment.
Oh, I'm like I said, we already have a point scheme, but like I said, light is a transverse and someday sound is a longitude.
Yeah, that's correct. All right, so the very first 2 points that you gave me, they're technically the same point. So if you're given a question, you want to avoid using those 2 points as your answer, because a vacuum is essentially a space with no particles. So it's a medium that light can travel through. Sound can't travel through it, again, because there are no particles for the sound wave to travel along. So you want to avoid using the fact that light can travel in a vacuum and the fact that light doesn't need a medium to travel as the 2 points but it's good that you mentioned the fact that the transverse and the longitudinal waves. And it ties in back what I was saying to you guys earlier. A lot of times the questions that they ask you, it contains some hints or they tie into the questions before it or after it. So they ask you about sound and light waves here. You can use the fact that we just mentioned about longitudinal waves to help you in this kind of question. And then this question is going to be a lens question. An object is placed 15 centimeters in front of a converging lens with a focal length of 10 centimeters. It says, I calculate the image distance, part 2, magnification, and then part 3, they just want us to state the nature and position of the image that is formed, right? So we know we're going to be using our lens equation, which says that 1 over the focal point is equal to 1, or focal distance rather, is equal to 1 over the object distance plus 1 over the image distance. And in order to use this question, you must use distance in terms of meters. So it has to be in meters for you to use this formula. You can't use centimeters, you can't use kilometers, it has to be meters, right? So we do a little bit of transposition and simplification here, and we're going to get our answer, well, not really an answer, but 3.333 per meter is equal to 1 over our image distance. Transpose and simplify, and we get 0.3 meters as our image distance, right? Next part of the questions ask us for magnification, which basically you can use image and object distance, or you're going to use the image and object height to determine the magnification. Now, for this question, we have both the image distance, or we calculated the image distance, and we have the object distance. So we're going to use those two values to get our magnification. Magnification is image over object, and so we get 3 as our answer. Now, please note that this value does not have a unit. It's unitless because meters in the numerator and the denominator cancel each other out. The image is going to be real and inverted. Now, this is something that I can't really help you with. It's just something that takes practice and a little bit of swatting to remember them, right? You just have to do enough questions and eventually you'll be able to tell whether or not the image is real, whether it's inverted and stuff like that, right? The diverging lens, it's always going to be virtual. Converging lens, it's dependent. So just do enough practice and you guys will eventually learn some of the ways to identify those. And there's something that, as I said, comes with time. Now, the final question on this paper, we're given another table. This time we're asked to identify circuit components, right? So for the filament lamp, that's what our circuit component looks like. It is essentially a circle, the line passing through it, but that line has a little bit of a semicircle on it, in a sense. Now, the second row, they're giving us the image right there. And from the image, you know that that's going to be a diode. Now, a fuse, there are many different representations of fuses. This is just one of them. So it's going to be a rectangle with a straight line passing through it. Kind of similar to how we represent a resistor, except that this one does not. Well, a resistor doesn't have the line passing through it, just connected to it, the rectangle, right? Next one is going to be our AC supply. Pretty easy, you know. This one again is a circle, and then inside of that circle, you have that wave in there. So you're gonna have our AC supply, or as they present it on the diagram, we're going to have that wave between two terminals, right? Now, I do think that the paper had a little bit of error there. In the last line of the table, you see they gave us cell and they gave us some diagrams as well. And the line above that is completely blank. So I believe cell should have been in the row above that. And the diagram remains in the current line. Cell, again, is a pretty standard circuit symbol that we use in everyday life. Essentially, it's two vertical lines with one, the positive terminal being a little bit longer than the negative terminal. And finally, this is going to be a variable resistor. And as you see, there are multiple representations of the variable resistor. Now, the manufacturer of a popular cell phone has upgraded the battery capacity to 9,600 coulombs. And if the standard charger can deliver a current of 0.8 amps, calculate the time taken to charge the battery. Now we have the charge and we have the current. We know that charge is equal to current multiplied by time. So it's a pretty simple calculation that we're going to be doing. Transpose to get the time, and our time is going to be 12,000 seconds, or roughly 3 hours and 20 minutes. Remember that in an hour there are 3,600 seconds. In a minute there are 60 seconds. Right. And then it says to calculate the voltage given that the power supply of the cell phone is 4.4 watts. We know that power is equal to current multiplied by voltage, or P is equal to IV. They want us to find voltage. So we transpose for that to get power divided by current is equal to our voltage. Plug in our numbers and we get 5.5 volts. And then finally, determine the work done to fully charge the cell phone battery. Now, our work done is going to be equal to our charge multiplied by our voltage, right? It's going to be 9,600 coulombs multiplied by 5.5 volts, give us 52,800 joules. Work done has the same units as energy, because you need energy to do work. And that is pretty much the end of the first paper. Any questions? We're a little bit ahead of time, so I can do a quick, can go back to any questions quickly if you guys want, or we can proceed to the next paper. Any questions?
No question, sir.
All right. Next paper that we're going to be looking at is going to be the 2019 paper. All right. So again, you're given a graph question. CXC loves to give you guys graph questions. Most of the times, it's the first question on the paper. And usually burns up a good amount of time for you to create a graph. You try not to waste too much time. And as I said, it's generally a good idea to read graph questions completely before starting those questions, right? Was this 2019 or this 2017 paper? Trying to remember. I'll double check and let you guys know later. One thing is the 2017 paper, and I just didn't change the wording right here from the last slide that I created. Right. Give me a second. Yep, this is a 2017 paper. This is the year that I did the exam. Right. So they're giving us our table right here, and say using a scale of 2 centimeter to 5 milliseconds on the horizontal axis, 2 centimeters to 0.5 volts on the vertical axis. Plot the graph of EMF versus time on the grid provided. We're going to use the graph to determine the induced EMF after 12.5 milliseconds and the time in milliseconds other than at the beginning of the experiment when the EMF was 0 volts. For this question, they've given you the scale that you're to use. But again, remember guys, you're free to choose whether or not you want to use the graph in a landscape format or a portrait format. You just need to ensure that you can show all the values on your graph on the paper that they're providing you with, right? Again, a limitation on my end is that I don't actually have a physical paper in front of me, and so I'm going to be using computer software again to draw my graph. It's not going to be on the same scale though, but we do have some idea what your graph is going to look at. So I'm going to show you these graphs first, and I'm going to ask you guys, what do you think is wrong with these graphs? Anyone? Or do you think the graphs are perfect how they are? Or you think
Like, I don't see the
no, that's not exactly what I'm looking for. This kind of question, I'm not looking for like whether or not it has title, scale, or units for this kind of question. I'm more looking for a conceptual answer as why is this representation of the graph wrong? not necessarily the graph and its elements like tied to scale and stuff like that wrong. Anyone wants to tell me why this graph is conceptually wrong?
There is because in the first one, it's because you connect the points.
You're hinting a little bit at what I wanted to get at, but kind of, yeah. I want to give it an next try. The two graphs are incorrect, by the way.
Third, the best fit wrong.
What's wrong with the best fit?
In the second one, like it only go through one of the points for the first, coming from 0.
All right. So the answer, or to let you guys know, the best fit line technically doesn't have to go through any point. It may go through a point. It may go through all the points. It doesn't necessarily have to go through a point. But I'll let you guys know conceptually why these two graphs are wrong. The reason why these graphs are incorrect is because they were drawn at straight lines. Voltage versus time, it's not a straight line graph, it's a curve. So you can't use a straight line to represent it, or you shouldn't use it. Unless specifically in that experiment that you are doing, you somehow control the voltage in order to give it discrete values at specific points in time. But generally speaking, voltage and time is a curve, so you don't want to use straight lines for this kind of graph right here. Right? Now, this is another representation that could be correct. Truth be told, I am still not 100% sure what CXC is looking for this graph in terms of the best fit curve, right? And I'm going to explain a bit, right? So there's a statistical technique that's called regression, right? That technique, it essentially finds the line that minimizes the total distance from all the points, right? So when you get a graph and you know you have the X and the Y coordinates and you plot them, that statistical tool, it finds the line that minimizes the distance, the total distance from all the points. That statistical tool is called regression. Now, the best fit line, it's an estimation of that line or the statistical tool. It's like you're eyeballing it and you're saying, I'm guessing that this line is the regression line because it seems to follow the data and it seems to minimize the distance. So best fit line, it's really just a guess as to what that statistical technique would produce, right? Now, when you have a curve like activity versus time, it's possible to modify that statistical tool so that instead of providing a straight line, you can get a curved line, like or activity versus time. However, in a case like this, where there are multiple curves, it becomes a bit more tricky and complicated, right? The best fit curve is very subjective in this case. Like, for example, if you're doing a graph of force and mass, you'd know that your gradient or the gradient of your best fit line should be acceleration or gravity, right? So that'd be roughly 10 10 meters per second squared. That's what you're looking for when you do an experiment. You do it in the lab, right? You're looking to get an acceleration of approximately 10 meters per second. So you know that when you do your experiment and you take the gradient and you get 15 or you get 20 or you get 5, you know that the answer is way off and there was some error in the experiment and you have to redo it over, right? But in a case like this where the best fit curve is very subjective, it's a little bit difficult to say objectively that this is the best fit curve versus that curve. It's a lot more difficult, right? And so it's likely that everyone's best fit curve is going to look completely different. On this graph here, I've shown you 2 examples of what best fit curves could possibly look like, right? And if this is what CXC wants, then that means that for this question, you're going to mark everybody based on the best fit curve that you've given, right? Remember, don't use a straight line, it must be a curve, and you're going to mark it based on that. And based on that fact, everybody's going to have a different answer, and it might be a lot more different than what you had anticipated. Someone's best fit curve, for argument's sake, might look something like this. Right? And it's very subjective. The year that I did, I knew a lot of persons coming out of the exam, they weren't sure what to do. Several persons did straight line graphs, and that's why I took the opportunity to show you guys what the straight line graph is and tell you not to do that, right? So for graphs that are actually curves, don't use straight lines. And for graphs that are straight lines, don't use curves. But yeah, as I was saying, this is just an example really of what potential best fit curves could look like. And as I said, the curve doesn't have to go through all the points. It may go through some, it may not as well, right? And so I'm going to be using this graph for the sake of explanation, but I honestly think that this best fit curve is more of what CXC is looking for. Just for the sake of explanation, I'm going to be using this graph to continue the question and read the value from it, right? So if you don't learn anything today, you must learn that don't use straight lines for curves and curves for straight lines. So the question I'd asked was to determine the EMF after 12.5 milliseconds and the time when the voltage was 0 seconds. Based on this graph, the EMF after 12.5 milliseconds, it's roughly 1.5. If you're using these 2 graphs right here, it would be 1.5 or about 1.75 there, thereabouts. And then this one again, aside from initial point, what time is the voltage also 0? That is going to be about 27.6 somewhere there milliseconds. Any questions? Or we understand everything that has been said so far? Right, I'm going to take it that everyone is on the same page and
Yes, sir.
can proceed, right? Again, this was the very first question, and in 2017, the one question or the one topic that I didn't feel that I mastered completely was electromagnetic induction, and it was the very first question on the paper. So I'm saying this to say that I don't want you guys to take a gamble to say that you're not going to study electromagnetic induction because you know that it's not going to come, or because you're not good at it. Even if you're not good at the topic, at least try to read through it. You might not be able to get all of the marks, but at least read through the topic so that you can attempt it if you have time at the end of the exam, right? So don't take anything for granted. So Kevin, a physics student, conducted an experiment to determine the effects of electromagnetic induction. He used the following apparatus. They provided us with a graph and said the magnet is pushed into the coil with the north pole entering first, and draw on the figure 1 the direction of the induced current and the direction of the arrow on the galvanometer as a result of this motion, right? And a lot of persons have difficulty with this topic, and to try my best to explain it to you guys, right? So in order to answer this question, you need to remember Lenz's law, which states that the induced current, it's such that it opposes the motion creating it, right? You also need to know either the right-hand grip rule, or you need to remember that current always leaves the north side of the coil, right? So Lenz's law, the induced current, is such that it opposes the motion creating it. And then the right-hand grip rule, you can use that to determine the north side of a coil. And that current always leaves from the north side of the coil. You need to remember those three things, or a combination of at least two of them to get your answer. Just a pictorial representation here of the right-hand grip rule. As you can see, the thumb is pointing towards the north side of the coil, and the current is leaving from the north side. So based on the diagram and the experiment, our current is going to be traveling in this direction, and the arrow in the galvanometer is going to be that way. I'm going to explain a little bit better for you guys shortly. All right. So what I want you guys to think is that the coil, I want you guys to think of it as a magnet, but you don't know which side of it is north or south, right? Everybody's following me? You guys can see my diagram. Everyone can see the diagram, right?
Yes, sir.
Right, so as I said, think of the coil as a bar magnet, but you don't know which side is north or south. And remember, Lenz's law says that the current opposes the motion creating it, right? So when you push the magnet in the experiment into the coil, essentially what it's going to be doing is that you're going to be pushing magnetic field lines or magnetic flux into the coil, right? And it's this fact that you're changing how these flux lines cut the coil that's going to induce the current, right? You've seen it on my diagram where it looks as though the field lines are coming out of the magnet and going into the coil, said on the north side of the magnet, flux lines go outward. The south side of the magnet, flux lines come in, right? We haven't identified whether or not our coil, which end of the coil is north or south. So far, I'm just referring to the magnet that you're going to be pushing into the coil, right? So the flux lines from that magnet is it's going outward and into the coil, right? Again, I've added my little diagram there with the arrow to show you the direction of the flux lines, right? Now, this is where we're going to have to do some thinking and figuring it out for ourselves, right? I've added a little diagram here just to remind you guys how the field lines on a bar magnet work. As I said, it goes out from the north and it goes into the south, right? Now, if the end of our coil closest to the magnet is the south pole, what's going to happen is that magnetic flux lines are going to be pulled into that end of the coil, right? And so there's going to be no opposition right there, because from the north side of the magnet, flux lines are being pushed out, and then the coil, if that end is the south side, it's going to be pulling in those flux lines to it. So it's not going to be opposing anything right there. There's no opposition right there, right? Now, if it is that the end of our coil that is closest to the magnet is a north pole, there is going to be some amount of opposition taking place, right? Because from the magnet, it's pushing feed lines into the coil, but the coil itself is also pushing feed lines out from that end. So there's going to be an opposition right there, right? And because of the opposition, we know for a fact that the end of the coil that is closest to our magnet is going to be the north side of the magnet. And as I said, the current leaves from the north side of the magnet, right? And so north is right here, and south to be right here. Current is going to leave from this side, right? It's going to go around. And so that's how we get the direction of the current. Everyone get that, or do I need to explain again and go over?
Can you explain it again, please?
All right. Yes, I can. Give me a second. All right. So remember, in order to answer this question, we need to remember Lenz's law, which states that the induced current, meaning that there was no current in the system, in the coil, in the conducting wires, there was no current to begin with. And then the magnet is going to induce a current in the coil. It says that that current, it moves in a direction that opposes the motion creating it, right? And remember, the right-hand grip rule, you can use it to identify the north side of a coil, right? And you need to remember that the current always leaves from the north side of the coil. So now back to my diagram again. Start from the top. All right. So imagine that the coil is a bar magnet, right? But for that bar magnet, you don't know which side is north or which side is south, right? Coil is a bar magnet, you don't know which side is north, you don't know which side is south. And then we have the magnet that we're using in our experiment to induce that current, right? And we know that based on the diagram, the north side of the magnet is closest to our coil. So we're going to be answering the question from that frame of mind. All right. So what happens in the experiment is that you're going to push the magnet into the coil, right? And as you push the magnet into the coil, the magnetic field lines or the magnetic flux lines, they're going to leave the north side of our magnet and they're going to cut the coils, right, in our circuit, right? And Lenz's law says that the induced current always opposes the motion that is creating it, right? So the motion is pushing field lines into the coil. So the motion that you want is a motion that pushes field lines out of the coil, right? So if the side of the coil that is closest to the magnet is the south pole, what's going to happen is that it's going to be pulling field lines towards itself. It's not going to be opposing the magnetic field lines from our experimental magnet, right? It's not going to be opposing it, it's going to be aiding it, because the magnetic field lines that are being pushed out of the magnet are going to be pulled in by the coil if the south side of the coil is closest to our magnet. So there's no opposition in that case, right? Now, if it is that the end of the coil that is closest to the magnet is the north side of that coil, there's going to be some amount of opposition, because the north side of the coil is going to be pushing against the magnetic field lines from our experimental magnet. Remember, field lines always leave from the north side of the magnet, right? So when you push that magnet into the coil, field lines are going to be entering the coil, right? But if that is the north side of the coil, it's going to try and oppose or push back those field lines that are entering it, right? And that is how we know that that side of the coil is the north side, right? So the side of the coil that is closest to the magnet is the north side. And current always leaves from the north side of the magnet, right? And so when the current leaves from the north side of the magnet, it's going to travel around the circuit this direction, back into the other end of the coil, right? And so our galvanometer, which is going to be detecting the direction of current, is going to be pointing in that way, from left to right. Got it?
Yes, sir.
All right. Anyone? All right. I think I'm going to move on now. And then if anything, we can come back to it later. Now, the next part of the question asks us to explain why an induced current is produced, right? And as I said, as the magnet is moved towards the coil, more magnetic field lines from the magnet are cut, and it induces a current in the coil. So the rate of change is this topic is kind of physics level, sorry, CAPE level, but they expect it to have some sort of understanding of it. But essentially, when the rate of magnetic field lines cutting a magnet changes, then it causes a current. So because you're moving the magnet, it causes the rate to change in a sense. So more magnetic field lines are cutting the coil because it's getting closer and closer to the coil. And so that causes current to be produced. That current is going to be, as I said, in a direction that opposes the motion creating it. Right? And now, next question is, why is it necessary to use a sensitive galvanometer? It's pretty easy. You just detect small changes in the current. The more sensitive it is, easier it is to detect small changes. And then part IV basically asks us what's going to happen if you remove the magnet from the coil. So before, you were pushing the magnet into the coil. This time you're taking it out of the coil, right? And so even if it is that you didn't know how to do the first part of the question, and you remember Lenz's law, it means that any direction you picked in the first part of the question, you just pick the opposite direction in this question, right? So if it was going from left to right in the first part, when you're moving the magnet away, it's going to be going from right to left. And so that is going to be the direction or the current when you're moving the bar magnet away from the coil. State 3 changes or adjustments that Kevin could make in this experiment to increase the induced EMF. Anyone wants to make a guess or know the answer? All right, so the very first thing that Kevin could do is that he could use a more powerful magnet, get a bigger, more powerful magnet, and it's going to create an even greater voltage. The next thing that Kevin could do is that he could increase the number of coils of the wire, right? Not just in this case, but the more coils you have, generally it's the greater voltage that you get, right? So if it's 2 coils, then you're going to have more voltage than if you had only 1 coil. When I say coil, I don't mean like separate spirals. I mean increase the number of spirals. So on the diagram, there are 6 spirals there. So maybe instead of 6, you could put it to 10, or you could put it to 12 or 20, and that would increase the voltage. The third and final thing that Kevin could do is that he could increase the speed of the magnet. So if the magnet is going into the coil faster, it's going to create greater voltage as well. So increase the speed of the magnet, increase the strength of the magnet, or increase the number of turns of the coil. And finally, describe what will happen if the magnet remains stationary in the coil. If there is no movement of the magnet, then there will be no current. No movement of the magnet means that the rate of change that the rate that the feed lines are cutting into the coil is going to be constant. And because it is constant, there won't be an induced current, right? So if the magnet isn't moving, there's no current. While the magnet moves, there is current because you're changing how quickly field lines cut in the coil. No current is produced, so the galvanometer is going to show a 0 reading. Yes, and finally part D of the question, where they give us an AC generator, right? And the coil PQRS is connected to other components of the circuit, which allow the coil to rotate in the direction indicated by the small arrow. So it's going to be rotating clockwise. And it says draw on the figure the direction of the induced current if the coil rotates in a clockwise direction. 2, you want to determine the period of the rotation of the coil. If the period of the rotation of the coil is 0.02 seconds, calculate its frequency. And finally, they want us to sketch a graph of voltage against time. Remember, voltage against time is always a curve, it's not a straight line. All right, so I'm going to work part 2 of this question first, but that's the easiest part to do. Frequency is always 1 over period. Substitute and then we transpose, simplify, and we get the frequency is 50 per second. So you're going to get 50 turns in a single second, right? Again, this kind of question relies on your knowledge from before. I'm going to use a diagram again to explain this. In order to do this question, you have to remember Lenz's law again. And we're going to need Fleming's right-hand rule, right? Fleming's right-hand rule is the exact same as Fleming's left-hand rule, except the current flows in the opposite direction. So if with Fleming's left-hand rule, current would flow from left to right. With Fleming's right-hand rule, it's now flowing from right to left. That's the only difference. So Fleming's right-hand rule is a combination of Fleming's left-hand rule and Lenz's law, right? And direction of the induced current is going to be moving along PS, right? That's the direction of the current. So you have to move in that direction. And it's going to go around the circuit and come back up RQ. That's the direction that you'll be getting. And I'm going to explain it now, right? So Fleming's left-hand rule, you use it to determine the force on a current carrying wire that is operating in a magnetic field. So with the left-hand rule, there is a current flowing through a circuit, and that circuit is in a magnetic field, and you want to determine the force that's going to be acting on that conductor. So it's a force on a current carrying wire operating a magnetic field. For Fleming's right-hand rule, you use it to determine the direction of the induced current of a conductor. No current is flowing now, that is being moved through a magnetic field. So the uses are different. You just have to remember that for left-hand rule, you use it to determine the force on a current carrying wire. For the right-hand rule, you use it to determine the current of a conductor being moved through a magnetic field. Right, so to the diagram now. For my diagram, we're going to be viewing the experiment as if it's right in front of us. So you're looking at it from this direction. That's the diagram I'm showing you guys. Looking at it from this direction right here. So your eyes are going to be seeing this side of the magnet right here, this side of the magnet right here. Right? Right, so we have the north and our south magnets. Again, X means, well, let me not get to X first. So we have our north and our south magnets. Field lines are flowing from north to south. This is before the experiment begins now, guys. There's no current going through the wires, so there won't be a magnetic field around the wire itself. It's just a metal rod that is in the magnetic field, right? Now, if you begin to move that rod or the coil in a clockwise direction, so the half on the left side is going up, half on the right side is going down, that is the point for which there is going to be an induced current, right? And when that induced current is going to be flowing such that the current is going out of the plane on the left side, and the current is going to be coming from the plane of the paper on the right side. X means that current is flowing into the paper. The dot means that current is flowing out of the paper, right? So remember, you have the magnet, it's operating. There are two, well, there's a coil in between the magnet. No current is flowing, nothing is being done to the coil. Then at some point you begin turning the coil in the magnetic field, then that induces the direction, right? And again, you just have to use Fleming's right-hand rule. So you know your thumb is going to be for the force or the thrust. So T for thumb is thrust or force. The second finger on your right hand is going to be for the magnetic field, right? So, sorry, the first finger is going to be for the magnetic field. So F for first, thumb for thrust or force. First finger is for field, magnetic field. And then the second finger is going to be for the current. So using the right-hand rule, our first finger is going to be pointing from left to right. Our thumb is going to be pointing upwards. And then the direction of the second finger is going to tell us whether or not current is flowing in or out of the plane. If you do it with your right hand, you'll see that current is flowing into the plane of the paper, and that is why there's an X on that side. Now, if it is that we're considering the other half of the coil, right? Do it again. Magnetic field lines going from north to south, so that's going to be from left to right. The coil is going downward, so your thumb needs to point downward, and then your second finger is going to be pointing towards your body, so it's going to be coming from the plane of the paper towards you. Everyone get that? Or you want me to explain one more time?
Yes, you can explain that again, please.
All right. So, as I said, this is the experiment right here, right? And let us imagine that the experiment has not started as yet. So what you'd have is that you'd have two magnets, north, another magnet, south, right? And the ends of the coil, one coil right here, other coil, other end of the coil right there, right? This one is going to be PS. This one right here is going to be RQ. All right. So this is before the experiment has started. There is no current flowing through the wire, but you can't turn on and off the magnetic field. So there are always going to be magnetic field lines between the two magnets, right? There's no current flowing through the coil. The coil is stationary. Magnetic field from north to south, right? Now our experiment begins and the coil is going to turn clockwise, right? So that means that PS, which is this half of our coil, is going to go up and around, right? And RQ, which is this side of our coil, is going to go down and around, right? Now, once that motion starts, what's going to happen is that the coil is going to be cutting through magnetic field lines, right? And as it moves, it's going to be cutting through more and more magnetic field lines until it starts slowing down and it's going to start cutting through less and less field lines. It's going to be a cycle. So it moves, it cuts through field lines, cuts through less field lines, and it cuts through more, cuts through less, cuts through more. So current is going to be changing in a sense, right? But let's not get there. Let us go back to the point where we've just begun moving the coil. So PS is going to go up and around, RQ is going to go down and around. As I said, as you start moving it, because it's cutting or moving through magnetic field lines, it's going to induce current. Now you need to determine the direction of that current. And to do that, you need to use Fleming's right-hand rule, right? So your thumb is going to be for thrust or force. The first finger on your right hand is going to be for magnetic field direction. So first field, then the second finger is going to be for induced current, right? So we have the direction of our magnet is going to go from north to south. So you're going to rotate your hand so that your first finger is pointing in that direction from north to south. So from left to right. Now we're going to focus on PS, that half of our coil that is going to go upwards. Because it's moving upwards, you need to set your thumb so that it's pointing upwards, right? Remember, we're using our right hand to do this, not the left hand, because we're trying to find the direction of induced current. Because you're finding the direction of the induced current, you have to use your right hand to do this. So our first finger must be pointing from left to right. The thumb is pointing upwards because PS is going up and around. And then now we just need to look at our second finger to determine the direction of the induced current. If you use Fleming's right-hand rule, you will notice that your second finger is pointing towards your computer screen or pointing towards your phone screen. It's pointing away from your body, right? And because it's pointing away from your body, it means that current is going to be flowing into the plane of the paper. There's going to be an X right here, and current is flowing this direction. Current is flowing here, here, that direction, right? So now we're going to consider the other half of our coil, which is RQ. Again, the first finger we need to point it from left to right because that's the direction of our field. RQ is moving down and around, so the thumb needs to be pointed downward. And then we use the direction of the second finger to determine the direction of the current. That second finger, if you're using your right hand, should be pointing away from your computer screen or away from your phone screen, or it should be pointing towards your body, right? Because it's pointing in that direction, it tells us that the current is coming out of the plane of the paper. And so we represent that with a dot on our diagram. And so along RQ, current is coming in this direction. Got it?
Yes.
All right. So that is our first question on 2017 paper. That's basically a refresher on magnetic induction, electromagnetic induction. It's going to take a bit of practice for you guys to master it. As I said, when I did this paper in 2017, I did not fully master this concept, yet I still got a 1 on the exam. I didn't get everything right, I know that for a fact, but I got enough right to get a 1 with a straight A profile. So you don't have to master every concept, you don't have to get everything right to get a straight A profile, but you need to get very good grades to get a straight A profile, but you can still pass with getting okay grades or getting a good amount of the paper correct, right? This is only 25 marks out of 100. If you score 10 in this and you maximize on the other 75 marks, that's what, 85 out of 100, you're sure you pass the exam there. Right. Right, so I'm going to be moving on to question 2 now. Oh, wait, I forgot one part of the question, well, the diagram. So this is my sketch of the graph. I started the graph from the amplitude and not from the rest position. And my reason for doing that is more of a technical reason, right? The coil, once it starts rotating, it's going to go up until it's reached its maximum point, right? And once it reaches its maximum point, it's going to have to change directions and start going down. when it changes direction and start going down, the direction of the current is going to change as well, right? And so for that half of the rotation, it's going to have the same direction current. So see if I can just do a quick sketch. So this right here is going to go up until it gets to this point right here. All right, and then when it gets to this point right here, I'm going to color that point as red. Once it gets to this point right here, it's going to change direction and it's going to start going downward until it gets to this point right here, right? Until it can no longer go any further downward. When that happens, you're going to change direction again, and it is going to go upwards. So every half rotation is going to change directions, right? So even though in the experiment, it would have started at quarter rotation or it's in rest, as soon as that experiment begins, the voltage jumps to the maximum that it will be, because it's at this point along that journey that is going to be cutting the most field lines. When it's at either extreme at the top, at the bottom, it's going to be cutting the least amount of field lines, and it's going to change direction. Because of that, the voltage has to cross the zero line for it to change. So if it was positive, let's say 2 volts, before it got to the peak of its rotation or the absolute lowest point of its rotation, once it reaches that point, it's going to go to 0 and then it's going to change to negative 2 volts. That's my reason for starting the graph at this high point, and then quarter rotation later, it would cross the axis right here, 0. Half a rotation later, it would cross the axis again right here, and then a quarter rotation later, it's going to be right where it started there. That's my reason. It's more of a technical reason for starting the graph that way. The middle part of this paper, you don't necessarily need to worry about it. There's a diagram to show you guys the right-hand grip rule. Right. So question 2 is asking us yet again the difference between transverse and longitudinal wave. We defined longitudinal waves earlier, right? And so in transverse waves, particles vibrate perpendicular to the direction of wave movement, right? And longitudinal waves, as I said, move parallel to the wave movement. So in a sound wave, which is longitudinal, particles vibrate. If the wave is moving from left to right, the particles would move left to right as well. In a light wave, if it's moving from left to right, particles will be moving up and down. And that's why you get that crest and trough along those waves, right? Given examples of them as light and sound already. And then the arcs in the wave equation, they want us to write it in its correct format. So we know that velocity is equal to wavelength multiplied by frequency, or V is equal to lambda times F, right? And then they give us a pretty easy question just to plug and chug, right? Calculate the speed of the wave, and we get 250 meters per second. So the wavelength is 250 meters, frequency is 10 hertz, 2,500 meters per second. Remember, hertz is the same thing as per second. So 10 hertz is the same as 10 per second. So simple questions, I say, guys, you want to maximize your marks, and simple questions like these where they ask you to identify things or state laws, give them formulas, you want to maximize on that. As I said, anyone can make a mistake on a calculation. You can plus something when you should have minus it. You could have added an extra zero. Anything can happen when you're doing a calculation. So the amplitude of the wave, as I said before, it's going to be from our rest position to the highest point, right? And it's going to be those three arrows that I've indicated. Amplitude based on the graph is going to be 0.5 millimeters. You want us to convert that into meters, so it's going to be 0.0005 meters. You know, it's a simple division by 1,000. The period, which is how long it takes for a complete waveform, so from start to finish, difference between 2 points in phase. So you can start from 2 rest points in phase, meaning both of them are going up or both of them are going down, or you can use the difference between 2 crests or 2 troughs, 2 peaks, 2 minimum values, and you'll get 4 milliseconds. For argument's sake, let's use the crest. That's going to be 5 seconds for the second crest, 1 millisecond, and 5 milliseconds. You subtract that, you're going to get 4 milliseconds between those 2 points. Convert that to seconds, you get 0.004 seconds. Finally, frequency, which frequency is 1 over period. So 1 divided by 0.004 seconds is going to give us 250 hertz. So you're going to get 250 waveforms in a single second. Final question asks us to state one property of an electromagnetic wave. And the easiest one to use is that they all travel at the speed of light, which is 3 times 10 to the 8 meters per second. It also mentioned the fact that there are transverse waves. Wanted, they can travel through a vacuum. They have magnetic and electrical properties. Anything that you wanted to state. Question 3 now. Elements with unstable nuclei are susceptible to decay. What is meant by the term nuclear fission? Then we're to state 2 advantages of using nuclear energy. Part B says workers in nuclear power plants need to be extra careful on the job. State 1 precaution that workers in nuclear power plants need to take. Give 2 disadvantages of using nuclear reactors to generate energy. Side note, I just mentioned it because I saw something last night on social media where Dion Jackson Miller was interviewing somebody from the University of the West Indies, and they basically said that the university has a nuclear reactor somewhere on the compound, and it's been running for, I think, 40 years or 30 years now, and there's been no incidents to date. They don't use weapons grade uranium. They use a relatively safer version of the same atom, and it's been going on safely. So it is possible in Jamaica. It's not a very large nuclear reactor, but we do have a nuclear reactor in Jamaica, so that's good to know. Back to the question. Nuclear fission is splitting of large unstable nuclei into smaller, more stable nucleus, and you get energy as a byproduct. It is a result in the decrease in mass. All right, anyone want to give 2 advantages of nuclear energy? Hello? Anyone? All right, so a small mass can produce a large amount of energy. It's one plus. Another plus is that this form of energy production does not produce any harmful gases, no carbon monoxide or anything like that. Any kind of gases that aid the greenhouse effect or global warming. Now, a precaution is that you must wear your personal protective equipment at all times and handle radioactive substances very carefully. And the disadvantage is that the power plant usually has to be decommissioned after 50 years to mitigate contamination or to reduce contamination related issues. Radioactive waste is harmful to the environment, is another disadvantage. And there's also the potential for catastrophic devastation if there is a malfunction. So we get a similar equation to what we got before. This one, some simple stuff. So uranium isotope U-238 undergoes nuclear fission when struck by a neutron. Barium-139 and krypton-97 are emitted along with 3 neutrons as shown in the following equation. Give you the equation and they give you the masses of the substance, and they want us to state the value of P. So that's going to be the proton number of our barium element, right? So essentially it's simple math where you just need to make sure that all the protons are accounted for, all the neutrons are accounted for, but you don't need to worry about the neutrons for this particular question. So we're going to have 92 plus 0 is equal to P plus 36 plus 3 times 0, right? And we end up getting P is equal to 56. So our barium has 56 protons. State the meaning of C in Einstein's equation. Well, that is the speed of light, and then calculate the total mass of the elements formed after the reaction. So the mass is equal to the sum of the end products. So we're going to be reading the values from our table and just adding them. Remember that there are 3 neutrons, so you have to multiply that by 3, and you get the mass as 390.19 times 10 to the negative 27 kilograms. Calculate the energy released in the equation. Remember, guys, in order to do this kind of question, we need to calculate change in mass. We have the final mass, so to start, we need to find the initial mass, right? And we get 400.02 times 10 to the negative 27 kilograms. The change in mass is 9.83 times 10 to the negative 27 kilograms. And then we just plug and chug into Einstein's equation. And get 8.847 times 10 to the negative 10 joules. And we use it for nuclear energy. Pretty simple. Use it for energy, electricity generation, nuclear energy. Same difference. Any questions here, or we're good?
Good.
All right. Question 4. All right. For a popular amusement park ride, patrons board a carriage at the top of a high tower and are subjected to a wild ride of terror. Name and state the Newton law which applies if the carriage is moving horizontally at a constant speed in a straight line. Anyone wants to tell us which law that is? Keyword here is constant speed.
The second law?
No, no, the second law is the one that has to do with momentum, change in momentum.
Oh, yeah. Is the law that improves force is equal to m times a?
Yeah, that's the second law.
Sir, is it the law of inertia, the first one?
Go again? Yes, law of inertia, first law. So that law says that an object or body continues in its state of rest or uniform motion in a straight line unless acted upon by a resultant force. So if a ball is rolling, it's going to continue rolling in a straight line unless there is some force acting upon it, some resultant force causing it to stop rolling. Typically, in a real life situation, friction is going to be acting on that ball, so it's going to stop rolling eventually. But in the absence of friction, it would theoretically roll forever, right? And if the ball is sitting still, no forces are being applied to it, it won't just start rolling without someone pushing it, moving it, or being shaken. Something would have to happen to cause that ball to move. So that's the law of inertia, or Newton's first law of motion. Now, the second part that asks us what law is taken into consideration when the carriage is in a free fall, that law is going to be our second law. Force is equals to mass times acceleration, or the rate of change of momentum. So that is Newton's second law. So bonus question. Anyone remembers Newton's third law?
Yes, sir.
What's that one says?
Every actional force has an equal but opposite reactional force.
Correct. So equal and opposite reaction forces, right? That is Newton's third law. There is a question on the 2016 paper that essentially requires you to use that law in its explanation. That's a question that speaks to whether or not an aircraft, well, speaks to an aircraft being in motion. It flies because of equal and opposite forces acting upon that aircraft. So you have lift and the weight of the aircraft acting upon each other to keep it at the same vertical height. And then you have drag and thrust acting upon that plane so that it can move at a constant speed. Let's continue. So part B says calculate the length of time that the carriage in part A on page 14. 14 is allowed to free fall if it reaches a speed of 64.8 kilometers per hour from rest. Important things to note, anytime you say free fall, means acceleration is due to gravity. Rest means 0 meters per second. Because how the question was phrased, you know that the initial speed is 0 meters per second squared. It reaches a speed of 64.8 kilometers per hour. So that's going to be our final velocity. We don't have any distance and we're asked to calculate time. So that pretty much gives us, or that indicates that the best formula to use in this situation is going to be V is equal to U plus AT, final velocity, equal to initial velocity plus our acceleration multiplied by time, right? But before we even get there, we have a problem. Our units don't match. Final velocity in kilometers per hour and our acceleration meters per second or time second. So we need to get those things to match. So the easiest thing to do here is to convert kilometers per hour into meters per second. In 1 kilometer per hour, there's going to be 1,000 meters and 3,600 seconds, right? Per hour just means 1 hour. So 1 kilometer per hour means 1 kilometer divided by 1 hour, or 1 kilometer divided by an hour, right? And then we simplify that fraction to get 1 kilometer per hour is the same as 5/18 meters per second squared. The question didn't ask us about 1 kilometer per hour, asked us about 64.8 kilometers per hour. So we're going to multiply that and we end up getting 18 meters per second as our final velocity. We're going to use the formula now. We're going to plug, chug, and transpose to get our time is equal to 1.8 seconds. So 18 meters per second squared is equal to 0 meters per second plus 10 meters per second squared multiplied by time. Time is 1.8 seconds. And then the last part of the question asks us to determine the distance that the carriage falls in B. Now, probably the easiest way to do this question is to use average speed multiplied by time. Average speed is the same thing as initial velocity plus final velocity divided by 2, multiplied by time, and you solve. Another approach should have been to use S is equal to UT plus half AT squared, where A for acceleration is going to be gravity, T is going to be the time that we just calculated as 1.8 seconds, U is going to be 0. So you could have used that to find the answer. There's also another equation, I believe it's V squared is equal to U squared plus 2AS. You can use that formula to find the distance as well. But in my opinion, this is the easiest way to do it. And you get the distance as 16.2 meters.
Excuse me, sir.
Yeah, go ahead.
Earlier on you said something about if they say it's free fall, we should assume something, but I did not catch that part.
Yeah, if they say free fall, it means that it's accelerating due to gravity. So you're going to use 10 meters per second squared or 9.8 meters per second squared. But the question said that we're to use 10 in this case. So once it's free fall, you always assume acceleration is due to gravity.
Okay, thank you very much.
No problem. Any other questions? All right. So we're at question 5. 4 factors of a surface of a material on which the absorption and emission of radiation depend are texture, nature, color, and area. State with a reason the appropriate characteristics of 2 of the above factors in the design of a car radiator and a roof of a Caribbean home. For part 2, when I say the roof of a Caribbean home, it's easier for you if you assume that they're referring to a zinc roof instead of, let's say, a ceramic roof, you know, those nice fancy roofs, or the roofs that are just flat concrete alone. It's easier if you assume it's a zinc roof that they're talking about. So for the car radiator, it has a large surface area so that the rate of emission is higher, right? The larger the surface area, the faster it emits and absorbs radiation. Same thing if it is black or dull colored. Black objects, they absorb and emit radiation a lot easier than white or silvery objects, right? And now for the zinc roof, it's going to be shiny so that it can reflect radiation easier, right? And it's a large surface area so that the rate of reflection is higher. So the surface area affects the rate that emission, absorption, or reflection takes place. If it is black, means that it is a good absorber and a good emitter, but it is a poor reflector. If it is shiny, it is a good reflector, but it is a poor absorber and a poor emitter. If it absorbs something well, it will emit it well as well. And goes without saying that the smoother something is the easier it is to reflect. That's why your mirror is made flat and smooth, so it reflects light easier. All right, part B. The following data were observed in an experiment using an immersion heater to determine the specific latent heat of vaporization of water, the mass of a can, and the water at start of boiling. M1 is 0.28 kilograms. The mass of the can and water at the end of boiling is 0.26 kilograms. The power of the heater is 150 watts, and the time of heating is going to be 5 minutes. Using the data above, calculate the specific latent heat of vaporization of water, assuming negligible heat is lost to the surrounding, right? So when it comes to a change of state, there is no change of temperature because all the energy or all the heat that is provided is used to break the molecular forces or to create those molecular forces between particles. So the particles themselves, they don't get faster, or they don't become hotter, or there's no change in energy levels for the individual particles themselves, right? So in this case, our electrical energy is going to be equal to our heat energy, because the electrical energy is being provided to heat the water. And so electrical energy is going to be equal to power times time. And heat energy is going to be equal to the change in mass, or it's going to be the mass of the water that changes state multiplied by the latent heat of vaporization, latent heat of vaporization. Right? So we simplify, we transpose, and we get our answer as 2,250,000 joules per kilogram. Remember, power times time is energy, that's measured in joules, and kilogram is in the denominator, so it's per kilogram. This is a specific latent heat of vaporization. Specific here means per kilogram. Can also be represented as 2,250 kilojoules per kilogram. Next part of the question says, the coils of the immersion heater was not completely submerged. Explain how this would have affected the values for the specific latent heat of vaporization obtained in BI. Anyone wants to take a guess here? As to what would happen if the coils of the heater wasn't all the way down into the water?
So some heat will be lost to the environment.
Yep, that's correct. Heat would be lost to the environment. Right? And in that case, there would be no negligible, the heat loss would not be negligible, and you'd have to factor it in. And because some of the heat is being lost to the environment, it's going to take a longer time for the water to be converted to steam, and so it's going to affect a lot of the calculation. Calculation is going to become very unreliable. Final question on this paper is going to be this one. So we're starting off with some lens here. Pretty simple question. I just ask you to give a diagram, the converging and the diverging lens, and you're to define the principal focus. The principal focus is the point through which all light rays pass or they appear to come from. The light for the converging lens, or the light rays would pass through that point. For the diverging lens, or the light rays would appear to come from that point, right? And so I've given you guys diagrams here so you can see what they look like. Converging lens, all the light rays would pass through that point, right? And for the diverging lens, if you trace the path of the light rays backwards, it would appear as though it's coming from a point that it doesn't actually come from. That's why the image for a diverging lens is virtual, because it appears to come from a point that doesn't actually come from. An object of height 7.2 centimeters is placed 18 centimeters from a converging lens of focal length 12 centimeters. Determine the image distance, the magnification, the height of the image form, whether the image form is real or virtual, right? So again, we're going to be using our formula. 1 over f focal length is equal to 1 over object distance plus 1 over image distance, right? Transpose that, we get 1 over f minus 1 over object distance is equal to 1 over image distance. We plug in our values and we get 2.778 per meter is equal to 1 over image distance. Transpose and simplify, and we get the image distance as 0.36 meters. Magnification, as I said before, it's always image over object. You can use distance or you can use height to determine magnification. And again, magnification is unitless because the meter in the numerator cancels the meter in the denominator, so we get our magnification of 2. And then we're going to use that magnification to determine our image height. Magnification times object height is equal to image height. 2 for the magnification multiplied by 0.072 meters. Again, remember guys, to use the length equation here, our distance and our height must be in meters. If you use it in centimeters, you're not going to get the correct answer. You can't do the conversion after it's done. You must use it in meters to get the correct answer. So you have to do the conversion before. And we get our image height of 0.144 meters is equal to our image height. And with that said, we are at the end of the second paper. Oh yes, image is real and inverted. And now, is there anything that you guys want me to just go back over quickly on this paper before we move on?
Yes, sir. The latent heat, sir.
Latent heat, that question?
Yes, sir.
What specifically about the question? Or you just want me to explain it all the way again?
Yes, sir. Go through it one more time. Thanks.
All right. So in this experiment, they're using an electrical heater to provide heat. Using the electrical heater because it can measure the voltage, the current, has a power rating, so you can quantify the energy. If you were to use it, so for example, a Bunsen burner, you wouldn't be able to quantify that energy readily. You wouldn't be able to say, oh, I supplied 2,000 kilojoules of energy with the Bunsen burner to cause a change in state. It could be done if you were doing a change in temperature, but because there's no change, because there's only a change in state, you need to determine the amount of energy required to change that state. You can't use like the Bunsen burner or a regular flame. You have to use the electrical apparatus because it's easier to quantify the energy that it provides, right? And so the immersion heater, so for simplicity, a quick sketch. Essentially what you'd have is something like this. A can here, you'd have the heater, something like this. Then you'd have the water above it, or let me use black instead. Water. This is our coil of the immersion heater. Can that contains water. And then here is our water. And that water is already at 100 degrees Celsius, right? But it has not started changing to gas as yet. So it's water at 100 degrees Celsius before it changes to steam. And you want to quantify, well, you want to determine how much energy would be required to change 1 kilogram of this water into steam, right? So the
Yes.
electrical energy that is provided from your heater is going to provide heat energy to create that steam, right? That's going to come off right here. And one electrical circuit can determine energy by multiplying power by time, or if you have the current and the voltage and the time, you can multiply those three quantities to get electrical energy. So 150 watts multiplied by 5 minutes. You have to convert that 5 minutes to seconds first, right?
Yes, sir.
And that is going to give you the energy. Now, as I said before, that electrical energy is supplied to the water at 100 degrees Celsius. It changes to steam at 100 degrees Celsius, right? Now, what you have measured in terms of weight is going to be the can or the beaker that you have and the water inside of it. It'd be very difficult for you to measure the weight of steam. It's a gas. It's very difficult for you to measure its mass directly. So what they've done is that they determined the mass before the steam, before it started steaming, and the mass after it started steaming. And so they're going to say that the loss of mass would have been the amount that was converted to steam, right? So this is a triple beam balance, right? And so if you subtract that, you're going to get 0.2 kilograms of steam was produced, and it's going to require LV worth of energy to convert 1 kilogram of steam, 1 kilogram of water to steam. So you need to determine LV, the specific latent heat of vaporization. If you were converting from, let's say, ice to water, the latent heat of fusion, right? But it's practically the same concept. There's no change in temperature, only a change of state. And so we're going to have ML equal to PT. And you're solving for L. So remember, this right here is going to be for energy, electrical energy. We have the mass right here. And if we want to find LV, we just divide those two quantities and we get this as our result.
Yes, sir.
All right. Any other questions?
No, sir.
All right. So I did not work out 2016 paper. That's more of like a discussion exercise for us before we go to lunch and then come back, right? So we are basically on schedule right now. is just if anyone has looked through the paper before and there's anything that they just want us to quickly look through. Again, we're given a time and activity graph here to do. We did something similar, so it's not that difficult. It's probably the same question. Looks to be similar. Here. Yeah, so right here, where they ask if to determine the first half-life, you know, we just have done one half-life calculation, and then we can use a table, use a graph to one half-life calculation. And for part 2, you do the average of 3 half-lives to get the more accurate value. You guys are seeing the screen, right? With the paper.
Yes, sir.
All right. I'm just going to be like skipping through the paper. As I said, if there's any question that you guys want us to look at specifically, you can just discuss it briefly and then we head for lunch. This was a question that I was talking to you guys earlier as it relates to Newton's third law of motion. There are 4 forces acting on the plane: weight, lift, thrust, and drag. But it's the thrust and the drag that's really important for this question. Pretty much a heat question that we saw before. For part A, this is where there's a change of temperature. For part B, that's similar to what we did before with the latent heat of vaporization or latent heat of fusion. Part C is basically method of mixtures. So it'd be like the heat energy that is gained by the ice would be equal to the heat energy that was lost by the water. And basically simplify and solve. So that's basically like common knowledge. Just these 3 of them. It would be good to just refresh that part of the syllabus, electromagnetic waves. Basically, I did a question like this in the past paper. In 2016 paper had a lot of heat-related questions. I can also look into like alternate sources of energy as well, just background information that might come in useful for the exam. Is there anything that you guys had specifically, if you've looked through the paper and you want to ask any specific questions? Or
Somebody in the chat said, how would you answer B? I'm not sure.
B, which B?
If it's the first question in section B, I'm not sure.
Can you first just specify which question? And remember, I can't see the chat, so you guys have to speak and let me know. I'm assuming that I answered the
Sir,
question.
sir, it's that one, sir, the wavelength, I think.
Oh, the wavelength.
Yes, sir.
All right, let me see. This is not particularly difficult. You just have to remember that all electromagnetic waves, they travel at the speed of light. So you're going to be using V is equal to F lambda. You're basically doing the calculation twice, right? Remember that V is going to be a speed of light. So same thing as C is equal to F lambda, right? You're going to have 3 times 10 to the 8 divided by frequency equal to your wavelength. So you, as I said, you essentially do this calculation twice, once for the frequency of the rattlesnake, the other for the frequency of the honeybee. Let's see. Oh, and this question actually highlights one of the problems that I was saying. If you don't know your calculator, you'll get a question wrong, right? So if you realize both of these numbers, they're in what's that, scientific form, or they give you times 10 to the negative some number. If you don't understand the syntax of your calculator, what it might do is that it might just divide by the first number and then multiply by the other half of the number. So let's know the example. There are some calculators that come with fraction functions. If you have the fraction function, it'd be better to use the fraction function to put this in your calculator. Or you'd have to use a bracket if you write it with the division sign. If you don't use it with the division sign, as I said, you might get the question wrong. Let's see, I'll just do the first one for you guys. It's 10 to the 8 divided by 3.5 times 10 to the 14. So you should get 8.57 times 10 to the negative 6, 7, negative 7. Yeah. What I was saying is that if you don't know how your calculator works and you just type it in one straight line as 3 times 10 to the 8, you use a division sign, and then you just wrote 3.5 times 10 to the 14, the calculator might give you an answer like 8.57 times 10 to the 21 power. What would have happened in that case is that the calculator would have divided 3 times 10 to the 8 by 3.15 and then multiply the result by 10 to the 14. Right? So if you don't know the syntax of your calculator, it can give you problems like that. If your calculator does not have the fraction function where you know you have 2, the bar, and then, for example, 4 below it, then what you'd have to do is that you'd have to put that 3.5 times 10 to the 14 in a bracket for it to give you the correct answer. If you don't put the bracket, you get the wrong answer. But yeah, that's basically how you'd solve the question. And you'd do the same thing again using the frequency of the honeybee, 1 times 10 to the 15, and you'll get the answer in meters per second. Sorry, meters, sorry. Any other question? Any other questions? Are we good?
Yes, sir. Good, sir.
All right, so the time right now is 12:27. Are you guys okay with half an hour for lunch or what? All right, so half an hour. So we'll come back at 1 o'clock for the remainder of the session, which is going to be focused on paper 1. So I'll see you guys in a few minutes, in half an hour, actually.
Yes, sir.
So quickly. All right, good afternoon, guys. Are you still here with me, hearing me?
Yes, sir.
All right, all right. So we're gonna continue with the paper one segment of our session. All right, I think I'm gonna give them probably a minute more and then we'll start. All right, so let us begin. First paper we'll be tackling is June 2022 paper, right? So the very first question refers to the following measuring cylinder, which is used to determine the volume of a liquid. The volume of the liquid is, and we're given the options, right? When measuring from the measuring cylinder, you always read from the bottom of the meniscus. And so our reading is going to be 7.5 centimeters cubed. So we're going to get B for that answer. Right? Given that force is equal to mass times acceleration, the unit of force can be written as A per kilogram meter second squared, B kilogram per meter second squared, C kilogram per meter per second squared, and D kilogram meter per second squared. What's the answer?
Sir, D, sir.
B, yeah, that's correct. Part 3. Let's look at the diagram. So it refers to the following diagram, which shows two forces, X and Y, applied onto an object. What should be the magnitude and direction of the third force, which causes the object to remain stationary, right? So X and Y, they're pushing the object from the left to the right. If the object remains stationary, therefore the resultant force and the object must be 0. So we're going to need an equal and an opposite force to counteract that, right? So the force has to have a magnitude of X plus Y. So that leaves either B or D, and it has to go in the opposite direction, right? X and Y, they're acting to the right. So therefore, the result, well, the other force that causes the box to remain stationary must be acting to the left. So our answer is B. Question 4. A diving ball is used at great depths, and so its walls are made thick. The main reason for this is that A, water pressure increases with depth.
Yes, sir.
B, water pressure increases with depth. I think that's a good answer. Let me just look through the others, see if anybody else have anything else to say. B, water is much colder at greater depths. C, a thin-walled vessel would float up to the surface. And D, density of water is much greater at great depths. Anyone disagrees with A? All right. So A is our answer. That is correct. Question 5. Which of the following statements about the object are true? I, it returns to its starting point. 2, it has 0 acceleration between times t2 and t3. And 3, its velocity at t4 is the same as its initial velocity. So this is a velocity time graph, right? Velocity is on the y-axis, times on the x-axis.
Sir, C.
So you say our answer is C, which is 2 and 3 only, right? That's correct. It has 0 acceleration between times 2 and 3 because there's no change in velocity. And its velocity at t4 is the same at time 0, as you can see from that horizontal line there. Now, from this graph, we cannot tell if the object returned to its original starting point by this alone. We wouldn't be able to determine that from this graph alone. The answer is C. The unit for momentum is kilogram meter per second. So we're gonna have B, right? A 4 kilogram mass is traveling at a constant speed of 5 meters per second. It is brought to rest in 2 seconds. The average force acting on it to bring it to rest is?
Sir, would it be
Force.
C?
C. Yes, C is correct. 4 is equal to mass times or acceleration. Mass is going to be 4 kilograms. Acceleration is the rate of change of velocity. So that is going to be, yeah, going from 5 to 2, 5 to 0, 0 minus 5 divided by 2. We simplify that and we get 10 newtons. Question 8 refers to the following diagram, which shows a non-uniform bar pivoted at P. W indicates the weight of the bar, and force F1 and F2 are applied at the position shown. Some of the clockwise moments about P would be equal to, no, if P is our pivot, right, then F1 is going to turn it in that direction, up and around. W2 is going to turn it down and around, and F2 is going to turn it this way. So the sum of our clockwise moments has to be F1 times D1 plus F2 times D2. Answer is going to be D. Question 9. The pressure due to the water is greatest at Q, R, S, and
A.
T.
Q.
Q? All right, where's the A?
Sir, why am I say Q?
Yeah,
Sir, because it's at a greater depth, sir, from the surface.
that's correct. A piece of string is tied onto a small stone, and then the stone is totally immersed in water. The tension in the string will be A, 0, B, equal to the weight of the stone, C, less than the weight of the stone, and D, more than the weight of the stone. The answer is C. There's a downward force acting on it, which is going to be the weight, and there's an upward force acting on it, is going to be our up thrust. So the resultant force that pulls the string downward is going to be W minus U, going to be less than W. Has to be less than. Question 11. Which of the following properties remains unchanged in a substance with an increasing temperature? Clearly, the answer is going to be A. Temperature does not affect the mass of an object. Temperature affects the volume of an object. The more it is heated, the more it expands. And if volume changes, density will change, because density is mass over volume. So if volume changes, density changes. Relative density is the density of an object in comparison to water, right? So if the density is changing, the relative density will also change. So the only answer that's correct is going to be A. Right? Remember, guys, if you type in things in the chat, I can't see it. So it's best if you open your mic if you have something to say or ask a question. Right? Question 12. When a ball is thrown vertically upward and reaches its maximum height, it has A, maximum kinetic energy and maximum potential energy, B, maximum kinetic energy and minimum potential energy, C, minimum kinetic energy and minimum potential energy,
Sir, D,
and
sir.
D is going to be maximum potential energy and minimum kinetic energy. Based on the answers here, D is the correct one. D is only answer that's correct. Remember, potential energy and kinetic energy, they're always changing from one to the other. So it's not possible for the two of them to be maximized at the same time. If you have maximum kinetic energy, you're going to have minimum potential energy. And if you have minimum kinetic energy, you're going to have maximum potential energy. Now, potential energy increases with height. And so as it reaches its maximum height, it's going to have its maximum potential energy. Now, 13. The time period of a single pendulum oscillating with a small amplitude depends on A, force at which the pendulum is set into motion, B, amplitude, C, length of the pendulum, or D. What's the answer?
C, sir.
C, length of the pendulum.
Yes, sir.
Anyone agrees or disagrees with that?
Agrees.
Agrees. All right. I don't recall if this formula is from Csec or from physics, from Cape Physics, sorry. But the formula is period is equal to 2 pi square root L over G. Oh, everything is under the square root, by the way. So length is the only factor that affects the period of the simple pendulum. Question 14. Based on the graph above, which are the following statements will be true? Simple Hooke's law question. The elastic limit of the spring was exceeded. Clearly that's true because you see where the graph starts to curve. Part B, the spring obeyed Hooke's law over its entire extension. No, that's not true. And part 3, force per unit extension in the elastic region was 7.5 newtons per centimeter.
Sir, B, sir.
B, 1 and 3 only. That is correct. To verify this, it's just 75 newtons divided by 10 centimeters, 7.5 newtons per centimeter. Which of the following is an SI base unit? Base unit refers to stuff like meter, ampere, seconds. Only answer here is going to be ampere. All the others aren't base units. Question 16 now. Which of the following implements are designed to take advantage of a large moment provided by a relatively small force? You have a crowbar, a claw hammer, and a pair of tweezers. What's the answer?
A.
A, 1 and 2 only. Anyone agrees with her?
Sir, I'm sure about the crowbar, sir, but I'm not sure where it's at.
All right. Anyone else? All right. So for the person that said A, you want to tell me why you don't think a pair of tweezers is a part of the answer? I'm not saying that you're wrong, I'm just asking. For me, I'm sure about crowbar and claw hammer. I'm questioning whether or not a tweezer is a part of the answer or not. So I'm between A and D. So I want to hear why you think a tweezer isn't a part of the answer.
Well, sir, a pair of tweezers doing a large moment, sir, I don't think so.
Anyone else? All right, so for me, all right, so a lever is essentially a device that takes advantage of moments, right? So in that case, if you're looking at it from the perspective of taking advantage of moments, then all three of them would make sense. And any mechanical device, it's supposed to amplify the effort that you put in. It's not supposed to cause it to exert more force than you need to. So if I'm looking at it from that perspective, I personally would say that all three are correct. But you have different types of levers, and different types of levers, they have for different purposes and they work differently. The crowbar, for 100% sure. The claw hammer, I'm 100% sure of. the tweezer. I'm still not sure if they consider that in terms of taking advantage of a relatively small force. They're basically using the tweezer to just clip something. So is it that they're saying that you're applying a small force to get a much greater cutting force, or what? So I'm still unclear about that one, if I'm being honest with you guys. But I 100% believe that crowbar and claw hammer is correct. I'm still on the fence as pair of tweezers, but if I had to make a guess, I'd go with A. All right, moving on to the next question. There are no attractive forces between the molecules in a gas. Attractive forces in a solid are very strong. In a liquid, it's weak, and in a gas, there isn't really any attractive forces. Which of the following statements about pressure law is true? The ratio of pressure to Kelvin, temperature is constant, volume is constant, or pressure is constant. The answer is A, 1 and 2 only. Pressure law is P over T. Therefore, pressure can't be constant. P over T is equal to K. It's the volume that is constant. (19) Which of the following ranges of temperatures is most suitable for a clinical thermometer? Answer is
Yeah.
D.
D.
Yeah. Question 20. The specific latent heat of vaporization of water is the energy required to change 1 kilogram of water at 0 degrees Celsius to ice at 0 degrees Celsius, or B, 0 degrees to steam at 100 degrees Celsius, or C, 100 degrees to steam at 100 degrees Celsius, or D, 99.9 degrees Celsius to steam at 100.1 degrees Celsius. Only correct answer here is C. When there's a state change, there is no change in temperature. Latent heat of vaporization is the heat energy required to change 1 kilogram of a substance from liquid to gas. And that occurs at 100 degrees Celsius in water. Question 21. The energy required to change the state of a substance is determined to be E subscript H. If the mass of the substance is doubled, the value of E subscript H will A, remain constant, B, be quadrupled, C, be doubled, or D, be halved.
B doubled.
Yep, answer is doubled. This is just a multiplicative change that this question is asking us about. EH is, came up as an N, but that should be an H, is equal to mass times L. If you double the mass, it's going to cause a doubling of EH. Right. A metal of mass M requires energy E to raise its temperature from T1 to T2. The specific heat capacity of the metal will be given by which one of the answers?
Sir, would it be D?
D is a dog.
Yes, sir, dog.
All right, anyone says C? All right, better let me ask you then, why not C? Why not C? Why D?
Sir, because sir, when you find the change in temperature, sir, would it be the final temperature? Might no, yeah, the final temperature minus the initial one.
Yeah, correct. If it is that you picked C for the answer, you're going to get a negative energy in this case. Or your value, the magnitude will be the same, but the direction will be different. And when you're raising the temperature of something, you're adding heat energy to it. That should be positive. When you're cooling it, you're removing heat energy from it. So that should be negative. That's why you have to pick D as the answer. Which of the following materials is both a good absorber and a good emitter of thermal heat? Remember, anything that is a good absorber is a good emitter. So A, a flat polished metal, B, a polished convex metal, C, a polished concave metal, or D, a flat metal plate painted black.
So D.
D.
D,
Yes, sir.
D as in dog.
Yes, sir.
Yes, sir.
All right, that's correct. For one, it's black. For two, it's flat and smooth. And for three, it's a metal. Part, well, A, it's polished, that tells that it's shiny, so it wouldn't absorb or emit radiation very good. And then B and C, it's not flat, it's curved. So that's going to affect how well it absorbs and emits right there. So 24 now. Specific latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. When 0.1 kilogram of water is converted into steam, it takes, or well, it absorbs or gives out energy. Let's answer that first, and then we see whether or not the exponent matches our answer.
Is it C?
C, it absorbs. That's what they say. Why absorbs and not gives out?
Sir, Mr. B, sir.
Yes, a B.
Yes,
All
sir.
right. All right. Why do you say B?
Sir, because sir, if it converted to steam, sir, more unlikely, sir, it will give off.
No.
I think it has to be A or C, but I can't see the tiny numbers.
All right. So for A, the exponent is 4. For C, the exponent is 8. But I'll just backtrack a bit. You are correct in thinking that the steam is hot, and so you'd want to think that you'll be giving off energy. But no, it actually absorbs the energy. And because it absorbs the energy, the particles or the steam is hotter. So it's going to absorb energy there. And it is, you are correct, the answer is C. Wait, give me a second. Let's look. 0.01. No, man, it's going to be A. Yeah, going to be 100. Multiply the two of them, that's going to be times -2. It's going to be A. So that's going to be 2.26 times 10 to the 4 joules for 24. It has to be absorbs energy. '25, which of the following diagrams best illustrates convection current in a liquid? Which one?
Sir, A.
B.
B. Anyone for C or D?
B.
No, like,
B.
sir, may I
B,
go with
sir.
D? Change it from A.
So B. All right, the correct answer is B. Yes. Convection currents are circular, but the difference between A and B is that in B, the heat is directly in the center of the can. So that's going to be the hotter part of the liquid, so that is the part that is going to rise. It's not like the left rises and the right falls, as in A. So it rises from the heat and then outward it falls. So B is more accurate.
So can you just re-explain number 24, why it's A?
24. All right, so specific latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram, right? When 0.01 kilograms of water is converted to steam, it absorbs 2.26 times 10 to the 4 joules. So we're going to multiply 2.26 times 10 to the 6, multiply that by 0.01, and it gives us 2.26 times 10 to the 4th power. So the exponent right here is 6. This, if you write it in the same form, is going to be 1 times 10 to the negative 2 power, right? So the exponent from this is 6. Exponent from this is going to be -2. 6 minus 2 gives us 4 as our exponent. When you multiply numbers,
Okay, I understand.
you add the exponents. When you're dividing, you subtract. You're welcome. So question 26 now refers to the following diagram, which shows water boiling at the top of a glass tube, while a piece of ice remains unmelted at the bottom. Which of the following statements provides a reason for this occurrence? A, the gas is a poor conductor of heat. B, water is a good conductor of heat. C, water is a poor conductor of heat. And D, glass is a good conductor of heat.
C.
C, that is correct. Water is a poor conductor of heat. That's why the heat only remains at the top of the water, the bottom part remains cold. And there would be no convection currents in this case because the hot water would rise and then the cold water that was initially at the top would fall to the bottom. But in this case, you're heating it directly at the top, so there's no cold water above it to fall down. So there are no convection currents taking place right here. So water is a poor conductor of heat. 27. 2 types of radiation, L and R, fall on a woman's left and right hand respectively. Her left hand feels hot, but does not become tanned. Her right hand does not feel hot, but it eventually becomes tanned. radiations L and R are. I have for this one D, infrared and ultraviolet. Anyone disagrees?
No, sir.
All right. UV radiation is what causes tanning. Infrared is hotter than ultraviolet because of the larger wavelength. A student carries out an experiment to determine the specific heat capacity C of a solid using the electrical method. Which are the following equations should be used? This is pretty much the same thing that we did earlier in the question, guys. So PT, well, similar, not the exact same formula, is equal to M C delta T or delta theta, and the transpose. So our answer should be C. P is the same thing as IV. So IVT, right? You need to divide by kilograms and you need to divide by the change in temperature to get the specific heat capacity. So the answer is C. Question 29 refers to the following diagram, which shows a transverse wave at a particular instant. The wavelength of the wave is equal to the distance PS, which is D.
Sir, yes, sir. B, sir. Sir,
Just to be
sir.
sure. Yeah?
Sir, wouldn't it be B, sir, from Q to S, sir?
No, man. It wouldn't be QS because those 2 points are not in phase. Even though S, let me see. No, it wouldn't be Q. Because this point right here, the point Q, well, better use. The point S would be right here in actuality. Just how they do it on the graph to show you the position along this horizontal line being S. So even the point S on the waveform is right here. This is the wavelength, this distance right here. P and S are in the same phase. Right? Q is at rest and it's heading downward. S is at the top of a crest. So it has to be PS.
Oh, yes, sir. I see it now.
Are we going too fast or everyone is following?
I'm following, so.
Following.
All right. Which of the following equations expresses the correct relationship between wavelength, lambda, speed, V, and frequency? So V, A. Yeah, that's correct. V is equal to F lambda. Transpose that to get F is equal to V over lambda. And you guys can clearly see why I decided to use a PowerPoint this morning. I don't like writing from a laptop. Never ends up looking good. All right. Question 31 refers to the following diagram, which shows an object in front of a plane mirror. Which are the following best represents the image produced by the plane mirror?
B.
B? Yep, that's correct. The image produced by a plane mirror will always be upright. The same distance from the mirror, the only difference is lateral inversion. But in this case, you wouldn't be able to differentiate any of these lines based on lateral inversion, so it has to be B. Same orientation as the image, the object, sorry. Question 32 refers to the following diagram, which shows a longitudinal wave where C and R represents compressions and rarefactions respectively. As the name suggests, compressions are where the wave forms are close to each other, rarefactions are where they're spaced out. If lambda is a wavelength, distance between C1 and R2 is 1.5 wavelengths C. C1 to C2 would be 1 wavelength. R1 to R2 would also be a next wavelength. The distance from C to R, from R to C will always be half of a wavelength. So it's 1.5. Compression to compression, rarefaction to rarefaction. Which of the following diagrams illustrates the law of reflection? Which is it?
A.
Sir, A.
All right, and if the question had asked you about the law of refraction, which one would it have been? No, refraction.
Sir,
Reflection is A, so we're good with that. But if refraction is the question, what would it have been?
Would refraction be D?
Yes, it'd be D.
Oh, okay.
Remember, it's always on the opposite side of the normal for refraction.
Oh,
Normal is going to be this perpendicular line right here. This is the normal right here. This is the normal.
yes, sir.
It's going to be on the opposite side of it. And it has to be in the other medium as well. Unless, of
Yes.
course, unless, of course, it's going to be a case where you have total internal friction, but that doesn't play in this question right here. Right. So which of the following properties is true of both light and sound waves? A, they're electromagnetic waves. B, they're longitudinal
They're D, sir.
waves. D, they undergo refraction.
Yes,
C,
sir.
they may be
Sir,
transmitted through
D,
a
sir, D.
vacuum. D is the correct answer.
Yeah,
All
please.
waves refract, reflect, diffract, and interfere with each other.
Yes, sir.
Right. So the following diagrams which illustrate the side view of a water wave. Wait, refers to the following diagram which illustrates the side view of a water wave. The amplitude of the wave is
Sir, what are we
A.
questions, sir?
yeah, go ahead with the question.
Sir, water wave would that be a transverse wave, right?
Yeah,
Okay, sir. Sir, 35 was C, right? Yeah.
you
I
say
say
C.
A.
You say A.
Wait. Yeah.
I say A because the amplitude, I think, is how high it goes. And since it goes about half of the 8, it has to be 4.
Yeah, answer is A. Remember, amplitude is from rest position. So it's from that 0 line right here. Has to be from this, so it'd be 4 up or 4 down. Amplitude is 4.
Yes, sir.
The refractive index of a transparent medium with a critical angle C for light traveling from the medium to air is?
Sir,
Oh, sir, that's something there.
sir.
All right, so I hear some person saying B. Anyone else have a different answer?
Oh, yes, sir. Yeah.
So you agree with B?
Yeah. Circle, right? Yeah, transpose and thing. Yeah.
Yep, that's correct. So it's going to be sine
Yes.
C
Yeah, equal 1 over the refractive index and the
One over
transpose.
minus
sine
sine 90.
Yeah.
Equals to 1 over the refractive index. And as you said, you transpose or you invert both fractions and you get sine 90 over sine C. (37) An explosion causes the emission of the following types of wave: light, sound, and infrared. Which of these will be received first by a person some distance away from the source? What's the answer?
Sir, infrared. So I think it would be the
Sir, I think it'll be
first. It would be light would
light
be first
before
because
sound.
light. Yeah,
A.
light that'd be light first. Then I think infrared goes before sound. Yeah, it goes before sound because it's the speed of light, right? Because never mind.
No, man, continue. Continue.
Wait, sir. Infrared that go before sound because EM wave when it travels at the same speed as air, or yeah.
Yeah, you're correct.
So it'd be light and infrared for the would be first, and then sound would be the last.
Yep, you're correct. So both light and infrared arrive at the same time. Because they travel at the same speed. 1 and 3 will be the first to arrive. And then sound comes after at a much slower rate. By the way, what's the speed of sound in air?
Sir, read that, sir.
What's the speed of sound in air?
Like 3.0 times 10 to the negative 8 or
Come on, that's the speed of light, man. Speed of sound, now on.
oh
Speed of sound is roughly 330 meters per second. So it's much lower than the speed of light.
yes, sir.
All right.
Wait, sir.
Yeah, go ahead.
So I didn't say, sir, which one would be received first by the person, sir.
Yeah. So it has to be light and infrared, but they travel at the same speed.
Sorry, so why?
Wait.
Sir, so, oh yes, sir, to see, sir.
Sorry, that's
Oh.
fault of the computer. It's
Oh,
B,
sorry.
but the box went around C. All right. So the note from a drum is louder when it is struck harder because sound waves produced have a greater what? Velocity, frequency, amplitude, or wavelength?
Amplitude.
Amplitude, that's correct. Loudness is to amplitude as pitch is to frequency. Speed and wavelength has nothing to do with this question. Now, 39, which line lies along the principal axis of the converging lens? JK, all right. Anyone disagrees?
No, sir.
Right. JK is correct. rectification can best be done using transformer, capacitor, transistor, or diode.
Diode.
The diode, sir. The diode.
Yep. So diode.
Sir,
Yeah, go ahead.
sir, you mind explaining, sir, what's rectification?
All right.
You know what I'm
you know-
just asking?
all right. So you know what is an AC wave, right?
Sir, what's the AC
You know what
wave?
is alternating current. You know it's an
Oh, yes.
alternating current. And you know what a direct current is, right?
Yes, sir.
Oh, AC
All right.
and DC.
So
okay.
rectification is a process by which alternating waves are converted to direct current. So essentially what it does is that it removes the negative portion of the AC wave. It's something that you learn in Cape Physics. They actually do it with 4 semiconductor diodes. It's arranged in a specific order. And based on how it's arranged, you know that diodes don't allow much current to pass in the reverse direction. So because of that, it basically creates a wave that only goes in one direction. So it's like a DC. You have things like half wave rectification and other forms of rectifications. But as I said, it's essentially creating a direct current or a current with only one direction.
All right.
That's
Yes, sir.
basically what rectification is. But as I said, you need about four semiconductor diodes to do it, if I remember correctly. So 41 refers to the following diagram, which shows an electrical circuit with a cell and 2 filament bulbs, which are the following circuit is electrically the same as the circuit above. So this is a series circuit, and we need to find another schematic representation that is the same.
C.
So the
C.
C
Yes, sir.
is correct. In any other instance that it's drawn, the current will be split before getting to the lamps and then recombined afterwards. (42) Given the following truth table with inputs A and B and output C, which logic gate does it describe?
Not and, NAND.
None. That's correct. So this is
So
kind of
why?
question.
We haven't learned about logic gates. Well,
Oh,
in my
as in
school.
here? Oh, it's not that difficult, to be honest with you. It takes a little bit of getting used, but it's not
Kind
that
of like
difficult.
IT one. Well,
Yeah,
there's something that it's true, or that true tape, I call it.
yeah.
Kind of like that.
To be
Yes.
honest with you, I don't think you'll be at a significant disadvantage. Either way you take it. If you look at it, yeah, you'd be good, but I don't see them asking you an entire written question. Like, for example, a paper 2, they'd probably only ask it like, give you like a 3, probably 4 marks, 5 marks at worst question. I doubt you're gonna get anything more than that on a written paper. But logic gates, pretty simple. It's just basically theory that you just have to remember the patterns and outputs. But for the NAND gate, it's a NOT AND gate. An AND gate produces a high output or a 1 when both or all inputs are 1. But for this example in front of us, you get a 0 only when both inputs are 1. So that tells us that they've applied a NOT to the AND gate. So the NAND gate is a combination of an AND and a NOT gate. The NOR gate is a combination of the OR and the NOT gate. AND gate, as I said, produces a high output only when all inputs are high. The OR gate produces a high output only when it produces a high output as long as one input is high. Logic gates, if you think about it in real life, you can understand it pretty simple, easy. If your mother says to you, John and Mary, come here, you know that both of you have to go there, right? And if she says, John or Mary, come here, you know that one of you have to go there. It's not that difficult, to be honest with you. It's something that you could spend probably 15 minutes just looking over quick and you'll be fine. Question 43. Oh, if you have any questions about logic gates later, you can always message me or send me an email. Question 43.
Sir.
Yeah, go ahead.
In 42A.
Sorry. Yeah, that's A. It's the box again. It's A.
All right.
Which of the following equations cannot be used to determine the power dissipated in a resistor?
B.
What you said? E?
B.
B as in boy?
Yes.
C or D.
No, it's C or D. Which one is it?
C.
All right, so we have one person saying C. Anyone else?
Yes, sir.
All right, C is correct. Now, power, whether it's in a resistor or not, is always P is equal to IV or VI, right? Now, we know from Ohm's law, V is equal to I squared. Sorry, IR. If you plug Ohm's law into this, you'd get I squared R, I squared R, right? But you can also write Ohm's law. If you transpose this for current, is going to be I is equal to V divided by R. And if you substitute for current into this, you're going to get P equal to V squared over R. So the only answer that is incorrect is C, but it has the fraction in opposite order. (44) Magnetic induction occurs when A, a north pole, attracts a south pole, B, an iron nail near a magnet becomes magnetized, C, a magnet is suspended and points in the north-south direction, or 3, an electroscope is charged. Answer is B for boy. Which of the following circuit symbol represents a fuse? Answer is
B.
B for boy. All right, question 45. Which of the following current time graphs best represents a DC current?
A.
A is correct. Oh yes, so what I was saying about rectification before is that this part of the graph here would no longer exist. If you had rectification, this part as well wouldn't exist. A is correct in this case, by the way. And again, if rectification was done on this graph, this part of the graph would not exist. That's basically what rectification does. Right. So 47, which of the following materials is more suitable for the core of an electromagnet? Only answer is D for dog, soft iron. Carbon and copper aren't magnetic materials, they aren't magnetic. Iron is the best metal for magnetism. 48, an ammeter has a very low resistance so that it can be placed in A, parallel with a component and not affect the circuit. B, series with a component and not affect the circuit. D, parallel with a circuit and not heat up. Or D, series with a component and not heat up. Which one is it? Parallel
B.
or series? You said B?
Series, but
Sir, so
C.
after BRD.
Right, so it is series, so it has to be either B or D, as you correctly stated. Correct answer is B, because you don't want it to affect the series, so it has a very low resistance. It's not likely that a substance with a low resistance, wait, let me not say that, because depending on the current, any substance can overheat. So 49. An ideal transformer has a primary, the secondary turns ratio of 1 to 3. An alternating potential difference of 20 volts is applied to the primary coil and a resistance of 200 ohms attached to the secondary coil. What is the current in the secondary circuit? We have A 0.33 amps, B 1 amp, C 1.5 amp, or D 3 amps. Which is it? All right, before we start a question, first I need to ask you guys, is this a step up or a step down transformer based on the turns ratio?
Step up.
Yep. Step up. All right, so we know that our transformer equations is this: NP over NS is equal to VP over VS is equal to IS over IP. All right, now using that equation or a pair out of those equations, can you guys tell me what would be the current in the secondary circuit?
Here B.
What you said?
B.
B as in boy?
Yeah.
Not quite. Right. So we know that the ratio is 1 to 3. So 1 to 3. Now we want to find the voltage in our secondary circuit. Voltage in the primary is 200. So the voltage in the secondary, which is VS, has to be 600. I'm shortcutting it, as it takes a lot of work to write out everything. So VS is going to be 600. And we know that VS is equal to IS times R. So we have 600 right here is equal to I times 200 ohms. Therefore, I is going to be
3 amps.
3 amps. A, that's correct. Remember, for this transformer equation, current is always flipped, as in the ratios. It's always a secondary that's in the numerator for the current. Everything else has the primary numerator. Primary term, secondary terms is equal to primary voltage over secondary voltage is equal to secondary current over primary current.
Sir.
Yeah.
So I've seen on past paper, sir, where transformers, sir, have worked a significant amount of marks.
I haven't looked back at all of them, but I don't think so. I've probably seen like 1 or 2 questions. I have to look back and tell you. I don't recall it though.
All right, sir.
That doesn't mean that you don't need to study it. It might be the one question, or it might be the very first question on your paper. Remember I told you guys?
True, sir. But
Electromagnetic
I haven't done it,
induction.
sir, as a topic, sir.
You still have what, 1.5 weeks? Doesn't take long.
All right, sir.
All right. Which of the following symbols represents the AND gate? The AND gate is going to be B.
B.
This is the NOT gate for my friend that hasn't done logics as yet. This is the OR gate. And then this is the NAND gate, which, as I said, is just a NOT gate combined with a OR gate. And you see that they put the little circle after the AND gate so that you can differentiate.
So these symbols will have to be memorized, right?
Yeah.
Okay.
Give me a second. All right, moving on to the next question. So 51 refers to the following diagram, which shows 2 resistors, R1, which is 6 ohms, R2, which is 4 ohms in parallel. What is the current through R1? If the current through R2 is 1.8 amps. All right. So what do we know about a parallel circuit? What do we know about the resistors in a parallel circuit?
One over total is equal to 1 over R1 plus 1 over R2 and so on.
Yeah, all right. What do we know about the current in a parallel circuit?
It splits up.
It's the sum.
Yeah, that's correct. It splits up. The total current is the sum of the current in all the parallel branches. And finally, what do we know about the voltage of parallel circuits?
It's constant.
Constant meaning that it's the same in all branches. That's what we're going to use to solve this question. If we can figure out the voltage in one half, then we'll know the voltage in the second half. And if we know the voltage and the resistance in the second half, we automatically know the current in the second half. So voltage is equal to I times R, so that's going to be 1.8 multiplied by 4. Someone do that math for me?
7.2, sir.
All right, thank you. 7.2. So we know that the voltage through R2 is 7.2. The voltage through R1 is also 7.2, right? Now, voltage we just said is the same in the parallel. So voltage is going to be equal to IR. And so therefore I is going to be equal to V divided by R, which is the same as 7.2 divided by 6, which gives us
1.2.
1.2. That's correct. 1.2 amps is our answer. So the answer is A. '52. Which device allows one circuit to switch another circuit on and off without any direct contact between them? Answer is a magnetic relay. So essentially what happens is that you'll have one circuit right here, another circuit right here. There's a magnet somewhere on this circuit. I'm not drawing it the best way. What's the best way to represent this? All right, let's see. Let's see that you have an L right here. All right. So let's say that current is flowing through this circuit right here. Current is flowing through this, and there's a magnetic material right here that's pivoted on a hook, right? There's a hook right here. The magnetic material is this L-shaped thing because electricity is flowing in our primary circuit. It magnetizes this, causes it to rotate, and then this arm comes up and hits that circuit, and it causes current to flow the second circuit. And when you turn off the current here, this rotates back away from the primary circuit. This drops down, and this circuit is now turned off. It's very difficult to show it in this format, but essentially that's what happens. This L here would be the relay, simplistic diagram. When you turn on a primary circuit, magnetism causes it to move, and the movement opens or closes the other circuit.
Sir.
Now, question 53. Appropriate labels for device W and XR. This is going to be a step-up transformer. We can tell that based on the number of coils. If the number of coils on the secondary wire turns are greater than on the primary side, it's going to step up and increase the voltage. If the number of turns on the secondary side is lower, it's going to step down and decrease the voltage. So this is going to be a step-up transformer, and X is typically from an AC supply. So the answer is C. Which of the following describes two properties of an alpha particle? No charge, very penetrating. Positive charge, very penetrating. Negative charge, not very penetrating. And D, positive charge, not very penetrating.
D.
D.
D is correct. Question 55. half-life is defined as time it takes
A, sir.
A. Time it takes half of the radioactive atom in a sample to decay. Right, that's correct. 56. The half-life of radioactive substance is approximately
2 days.
2 days. That is correct. Yeah, go ahead.
No, sir, I'm just agreeing with the 2 days.
Okay, all right. '57. The nuclide TH234 contains 90 protons and
144 neutrons.
that's correct. C. Bottom number is our proton number. Top number is our mass number. Mass number is a combination of the protons and the neutrons. So if you subtract these two numbers, you will get number of neutrons. 58. Which of the following statements about radioactive decay are correct? 1. It is dependent on conditions external to the nucleus. 2. It is a random process. And 3. It is due
One
to
and
changes.
not 1, 2 and 3.
B.
C.
B.
B.
C. C.
No, I meant C. C. I meant C.
Yeah, C is correct. External conditions don't affect radioactive decay. Chemical reactions don't affect it either. 59, which are the following statements about a proton, it is true. It is a hydrogen atom minus an electron. It has the same mass, that of an electron, as incorrect. Has a mass of about 200 times that of an electron. Yeah, that's about correct. And D, it has a charge equal in size
B is
the
incorrect.
opposite. Yep. So
Yeah,
B
B.
is the answer. Finally, on this paper, an isotope of uranium-234 changes to TH230. This is an example of which type of decay?
Alpha.
Alpha, is correct. We know it's alpha because the
So
proton
it's
number
4.
decreases by 2 and the mass number decreases by 4. Beta decay is essentially a neutron.
Oh yeah, 0 and 1, so it loses 1.
Yep.
Sir, the beta wasn't.
Right, it's an electron. It's supposed to be
No,
0 and
electron.
-1, right? Yeah, 0 and -1.
Yes,
So
sir.
I think it's an electron, not a neutron. Yeah, you're correct. Right. So we finished 2022. And then we're going to look at 2021, see if we can skip through, pick up any questions that we didn't see on the other paper, and just tackle those ones. Right. Question 1, power can be defined as
C.
C, work done divided by time, that's correct.
Yes, sir.
Errors due to parallax can be minimized by
B, sir. With the
taking the right angle. Sure, that's correct.
Oh, okay.
Yep. Which of the following pairs consist of fundamental quantities? Mass and weight, mass and length, time and current.
Mass and length, time and current.
Yeah.
Correct. 2
Yeah,
and
'cause
3.
weight is something. A
Weight is a force. It's derived.
Yeah.
That's correct. We did 4. Now 5 refers to the following diagram, which shows 3 forces of magnitudes L, M, and N, all in the same plane and applied on a ring. Which of the following equations must be true in order for the ring to remain stationary?
Sir, D, sir.
Yeah.
No, DC.
C as in cat?
No, sir, D. N equal L plus M.
Anybody has a different answer, or everybody says D is the correct answer?
B,
You say boy,
boy.
right? The correct answer is boy. And I'm going to show you why now. Let us calculate the resultant force here from L and M. We start with a box. This is L, this is M, right? And from geometry class, math class, we know that the length of this right here is going to be the square root of L squared plus M squared from Pythagoras theorem, right? So N must be equal to that. In order for it to stay stationary, N, which is acting in this direction, must be equal to the resultant force acting in this direction. And simple transposition of this gives N squared is equal to L squared plus M squared. So B is correct. If you had tried to do this question with any other pair of forces aside from L and M, to find the resultant of those two, it would have been much more difficult, but you would have gotten a similar answer. But if you attempted to do that, you'd have to take into consideration the sine and cosine of angles, and that's not really Csec level. So you do it the easier way. That just requires Pythagoras theorem. When you get to Cape, then you'll start using the cosine and sine. Part 6, which are the following changes can be caused by a force acting on a body: a change in shape, a change in motion, and a change in density. Which one? Or which ones?
The motion and density, right?
Shape and motion.
So I have shape and motion. I have someone say
No, it
motion
can't
and
change the
density.
density. That'd be one I. So would that be A?
A? That's what
Yeah.
you say?
Yeah, I think so.
Anyone disagrees, or everyone says A?
I agree.
I say A.
You say A?
Yeah, you can't change density. Go back.
They actually you can change density.
Force acting on it, sir.
Yep. Think of a sponge. If you crush it together, you have decreased the volume, but it's the same mass. So you change the density.
Oh.
Oh, yeah.
And if pressure, if you apply enough pressure to a metal, you can flatten it, or you can crush it. Well, probably metal is probably a bad example. It'd be better to use like a more porous material. You can crush things together, like for example, a car, you know, they crush the metal together, get it more dense. Yeah. The metal in its raw state wouldn't exactly be a good reference, but like a car, you know, you can crush that. A sponge, a piece of paper, you can crush it and get it more compact than its original state. So all three are possible. You can change its shape, its volume, its motion, its density. The mass wouldn't change, the volume would change. Part 7. So when the tap is open, water will flow from P to Q until
D.
as in dog. Water levels of P and Q are equal. That is correct.
So you could
We
explain
did
that, please.
this one. This.
Yes, sir.
All right. So essentially, what happens here is that there's a lot more pressure in this system, right? So the pressure acting right here is a lot greater than the pressure acting right here. And because of that difference in pressure, it's going to force water to go up and around and down. And as that happens, the water level here is going to decrease. Water level here is going to increase until they are both at the same horizontal level. There'd be no difference in pressure, and so it'd be at the same level. The water is going to stop at that point. It's going to stop flowing between containers at that point. So the
All right, sir.
pressure acting over here forces it around the system to this container. And when they get to the same height, the pressure is going to balance out. Question, did you guys learn anything about the YouTube manometer or so?
No, sir.
No, okay.
I've heard
Sir,
about it.
you can show me a diagram of it, sir.
I don't have one right now, but it's essentially something that operates on the same principle. It'd be like a bend, it'd be something like this. And then you'd have, I think sometimes you have like different,
yes, sir. Yes, sir, I did.
you have different densities of liquid in here, and it's trying to balance it out and pressure. I think they use something similar in car engines, if I remember correctly. But it's essentially the same setup. It's like a bend. You have liquids in there and different pressures and pressure heads and stuff like that.
Yes, sir, I did learn about it.
All right. So the kinetic energy of a body of mass m and velocity v is given by
D, sir.
d. That's
Dog.
correct.
Dog, sir. Yeah.
Half mv
Half of
squared.
mass times velocity squared. Yeah.
Which of the following will be constant if a constant net force is applied to the body? Kinetic energy, acceleration, momentum, or velocity. If there is a constant force acting upon a body, which one is going to be the same? It's going to be acceleration. Remember Newton's first law that says that a body at rest stays at rest and a body in motion stays in motion if there are no forces acting upon it. So because it's a constant force is acting upon it, you need to have a constant acceleration. If there's no forces acting on it, then its acceleration is going to be 0. Its velocity will also be equal to 0. Kinetic energy will also be equal to 0. Momentum will also be equal to 0. But if a force is acting on it, it's going to have a constant acceleration. The constant acceleration there is going to provide it with a velocity that may change. Well, should change depending on acceleration. If acceleration is 0, it won't change. If acceleration is more than 0, it will change. Question 11. Pressure in a liquid can be calculated using the formula P is equal to rho GH, which are the following sets of units will result in the SI unit of pressure.
What that, sir? That's a B. Yeah, you have wait 1 second, sir. Remember that's a B.
Yep, B is correct. Pressure is pascals, which is force over area. So it's going to be Newton over meter squared. And everybody knows that Newton is the same thing as a kilogram meter per second squared. And if you divide that by meter squared, you're going to get kilogram per meter per second squared. Kilogram here cancels a kilogram here. There's a 1 meter right here, and this is a per meter cube, so that's going to change to per meter squared. Newton per meter squared. Have our answer of B. An ice cube sinks in liquid A, but floats in liquid B. Which of the following statements is true of liquid A and liquid B? All right, so the fact that it sinks in liquid A means that the weight of the ice is greater than the upthrust that's provided to it in A. But if it floats in B, it means that the weight of the ice is equal to the upthrust. So therefore, we know that the upthrust in B has to be greater than the upthrust in A. So our answer is A. The pressure on the dam at the bottom of the reservoir depends on the mass of water held back by the dam, the volume of water held back by the dam, the length of the reservoir, the depth of the water.
Depth of the water.
Depth, that's correct. We did that one already. Now, from the graph, it can be deduced that the runner is going slower and slower, going at a steady speed, going faster and faster, and not
Steady
moving.
speed.
Steady speed, that is correct. Two forces of 8 newtons and 10 newtons cannot give a resultant force of. Which one do you think the answer is? All right, so the answer here is going to be A, right? When forces act in the same direction, you add them to get the resultant force, right? So if the two forces are acting in the same direction, it's going to be 10 plus 8, which is 18. So we can check that, right? Now, when two forces act in opposite directions, they work against each other, right? So if you subtract 8 and 10, you're gonna get 2. So if they work together, maximum resultant force is going to be 18. If they work against each other, the minimum resultant force is going to be 2. 9 is in that range. 1 is only answer that is outside of that range, so it has to be A. Understand?
Yes, sir.
All right. We did 17. What is the gain in the gravitational potential energy of a body of weight 200 newtons as it rises from a height of 30 meters to a height of 35 meters above the Earth's surface? That's the answer.
Sir, 40
Yeah.
joules.
Let me see.
Oh, yeah, times.
Yes, sir. C.
Sorry, sir.
You said C? C is correct. Yeah. You have to multiply them. So it's going to be the change in height multiplied by the weight. Change in height is 5 meters, the weight is 200. So we get 1,000 joules. Who was responsible for arriving at the conclusion that measured amounts of electrical and mechanical energy can be converted to proportional amounts of heat energy? Rumford, Coulomb, Newton, or Joule?
Sure.
Are you sure or are you guessing?
Guessing.
You are correct. Joule would be the best answer here because from you hear the name Joule, you know that he must have worked on something to do with energy. So it'd be most likely him. Newton most likely worked on force. Coulomb most likely worked on some sort of electrical component, something related to that. Rumford worked on the atom, if I remember correctly. He had a schematic diagram of what the atom should look like. Most likely answer is Joule, and the correct answer is in fact joules. Joules, sorry. We did 20 before. 21, we did that. Right, 22. A gas occupies 2 meter cube at 27 degrees Celsius at a pressure of 1 atmosphere. At a pressure of 2 atmospheres, it occupies a volume of 1 meter cube. What is the temperature at this new volume and pressure? Any takers, or you guys are calculating? You guys are calculating?
So is this the combined gas law?
That's correct. It is a combined gas law question. But if you look closely at the question, you will realize something. I'll let you guys continue working until you get the answer. Give you guys a few more seconds.
Questions, let me just come back.
Oh, 22. So a gas occupies 2 meter cube at 27 degrees Celsius at a pressure of 1 atmosphere. At the pressure of 2 atmospheres, it occupies a volume of 1 meter cube. What is the temperature at this new volume and pressure? Okay, should I just go ahead and tell you guys the answer?
Sir, wouldn't it be 27, sir?
27 is correct. Oh, you got 27.
Sir, when me do, sir, me just say the temperature would remain constant, sir.
You're correct. Yep. You didn't need to calculate this question.
Yes, sir, but we just that thing, sir, would it be correct or not?
The correct one, you're correct. For this question, if you realize the pressure and the volume, they basically switched values. So based on how the formula is set up, it's the product of pressure and volume divided by temperature equal to the product of pressure and volume divided by temperature. In the first half, the product of pressure and volume is going to be the same as the product of pressure and volume in the second half. Therefore, the two temperatures must be the same. So you didn't need to work any calculations for this question if you realize that fact. But if you didn't realize that fact and you work the question the long way, you might have made a mistake if you use the temperature as 27 degrees Celsius. When you're using the gas laws, temperature must be in Kelvin for it to work. If you use any other unit of temperature, it will not work. You can use any unit of pressure and volume, that's fine, but temperature must be in Kelvin for the gas laws to work. But yeah, the answer is B, 27 degrees Celsius. There's no change. Which of the following statements about evaporation is false? Evaporation occurs only at the surface. Evaporation requires heat energy and causes cooling. In evaporation, the faster molecules escape the liquid. And D, evaporation occurs at room temperature only.
D, false.
That's correct. D is false. Evaporation can occur at all temperatures. And it is when the faster or the molecules with more kinetic energy escape from the liquid and become a gas. 24, which of the following is the poorest conductor of thermal energy? Air, copper, mercury, aluminum. The obvious answer here is A for air. Metals are very good conductors. All the other three options are metals. 25. So molten naphthalene at 100 degrees Celsius is allowed to cool to room temperature if naphthalene has a melting point of 80 degrees Celsius, which are the following graph best represents the cooling curve of naphthalene.
C, sir, C.
C is indeed correct. It's 26. An electrical kettle full of water is plugged into the mains, this meaning plugged into the socket. The major process by which heat travels through the water is radiation, convection, conduction, or electrification.
Convection.
That is correct. Which of the following are reasons why a hot liquid placed in a double-walled vacuum flask retains its heat for a long time? Evacuated space between the double wall reduces the loss of heat by conduction. Silvered inner walls reduce the loss of heat by radiation. And silvered outer walls helps to absorb heat from the surrounding. Answer is...
Sir, A, sir, iron 2.
Yep, iron 1 and 2. That is the correct answer. Silver is a very poor absorber and emitter, so they would not use it if they wanted to absorb heat from the surrounding. They use it so they can reflect heat from the surroundings. As the temperature of a liquid rises, A, its density increases, kinetic energy of its molecules increases, the forces between its molecules increases, and D, the pressure it exerts at the bottom of the container increases.
Sir, B, sir.
B.
Kinetic energy of molecules increases, that is correct. And the density would decrease as it is heated. Remember, density is mass over volume. Volume increases with an increase in heat, therefore density would decrease. A light bulb is filled with a gas at a temperature of 293 Kelvin. If the initial pressure of the gas is P, what will the pressure be when the temperature increases to 360 Kelvin? Answer is
Sir, D, sir.
D as in dog is correct. We did 30 already, we did 31 already. All right, 32. The human ear is incapable of hearing a silent dog whistle because A, the dog whistle does not make a noise. C, speed of sound is too fast to be detected by the human ear. That's B,
Sir,
sorry, C.
Would it be D?
That's C. Yeah.
Someone says D, the waves are ultrasonic frequencies below that detected
Something
by
about
the human
frequency.
ear.
A D.
C.
Sir, D, sir.
No, a D.
All right.
It'll be lower.
Is it lower or above?
It'll be lower.
Sir, lower, sir.
Nope, it's
Well,
above.
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 Ah, sure.
It's above, man. Frequency is above that, what we can hear. A, sorry, 33, sorry. An echo is quieter than the original sound that produced it. This shows that compared to the original sound, the echo has
Loudness, so it's amplitude.
Yeah, small amplitude.
Yep, correct. We did 34. All right, a ray of light leaving ear enters glass of refractive index 1.6. The angle of refraction is 27 degrees. What is the sign of the angle of incidence? So we know that sine I is equal to sine R, which is going to be 27, going to be equal to refractive index of the second medium relative to ear is going to be 1.6 divided by the first medium relative to ear, which is 1 because it is ear. And so sine I is going to be 1.6 sine 27.
Let's see this transpose. So N is equal to sine I over sine C. So it's transpose thing.
Right, so this one. The 36, which are the following diagrams, best represents the wave generated in a ripple tank by a small spherical dipper vibrating at a constant frequency.
Sir, A.
Right, you say A, anybody has a different answer? Anyone think C?
Yeah, sir. C.
C,
Yeah.
right? Anyone thinks B? All right, so the answer is A. Because it's a constant frequency, the water waves are going to have a constant frequency as well. For C, it shows increasing frequency or decreasing frequency. Give me a second. Yes, so the answer is A. Everyone understand why? Constant frequency
Yes,
is a
sir.
key word.
Yes, sir.
Right, let's see. Which of the following statements about waves is true? Only transverse waves undergo reflection. That's wrong. Refraction can take place with light waves. Is that correct? All waves undergo reflection, refraction, and diffraction. Well, if C is correct, then B can't be correct. So we're in contention right there. And D, longitudinal waves do not undergo refraction, but may be reflected. So we're somewhere between B, C, and D. What do you guys say?
Cat.
Sir, C, sir. C.
All right, answer is C. Light does diffract, but the difference is that it's, well, not different, but it's just not easily noticeable because the wavelength of light is much smaller than the openings or corners of everyday objects. So it's a lot more difficult to observe. Longitudinal waves do experience refraction and reflection. Sound waves can refract and reflect, and you hear echoes. 38, which of the following objects can detect X-rays? Thermometers, oscilloscopes, television aerials, or photographic film?
Sure, that's an D that wait. A D, sir? I'm not sure. No,
D, sir. D.
D. I'm not,
I have B.
that's good.
Not A.
Wait,
It's
what?
definitely not A.
Not
That's
A.
right. The answer is oscilloscope.
Yo,
Sir, so what's
yes,
D used for, sir?
B was D, photographic film.
yeah, which
No,
one? I
sir.
don't know,
D,
said
sir.
use for one of the EM waves then, but which one, sir?
Probably, I know there is in a dark one, I don't remember. I thought you mentioned it, so let me see.
Hey
Let's
guys.
see. So the oscilloscope is a type of electronic test instrument that graphically displays varying electrical voltage. Yes. Okay, did I do this wrong? Let's see. You're probably right with the photographic film. You're right, it's photographic film.
Oh,
Sure.
Wait, sir, wait. 38, which one, sir? B,
It is D.
wait,
The
so
dark
wait,
photographic.
so what B, sir? Wait, which EM wave that are?
No,
like,
that's a different kind of tool. That's, I think, an electrical
all of
device. Someone's mic is open and is picking up the background.
Oh, okay, sir.
Yeah. Yeah, oscilloscopes, they're used to measure waveforms like voltage and time on different waveforms and stuff like that.
Wait, sir, question. What the name again? cathode ray.
Cathode ray tube.
Yeah, that's for gamma, right? The gamma rays thing. I'm not
Mm,
sure.
I don't recall, but I know that it has something to do with one of the electrical waves, as you mentioned.
Okay, sir. All right, sir.
Yeah. A ray of light in air strikes a glass block at an angle of incidence of 0 degrees. The light will be A, undeviated, B, totally reflected, refracted at 90 degrees to the normal for C, and then for D, refracted at an unknown angle.
Sir, is either. Oh no, incident. Sir, A.
A.
A is correct. Whenever light enters a different medium along normal, does not deviate. Remember, refraction is caused because there's a difference in speed. So one portion of the wave is in the slower medium, while the other portion of the wave is in the faster medium at the same time. So that causes the direction to change. If it reaches the next medium at the same point, there'd be no change in speed, or there's a uniform change in speed rather. So what you can do, you can imagine like a car that's driving along a road, and if there's a slant where this is asphalt, A for asphalt, let's use that, and then you have D for dirt. What you're going to have is that the tires on this side is going to be on dirt, while the tire on this side is going to be on asphalt. So if the car was coming this way, it's going to change direction and it's going to go this way, as the part on asphalt is going a little bit faster than that on dirt. It's going to change directions and refract like that. That's essentially what happens. Now 40, the position of an image formed by a planed mirror depends upon A, the distance of the observer from the mirror, B, the distance of the object from the mirror, C, the angle at which the image is viewed, and D, the angle at which the object is viewed. Which one is it? Answer is B for boy, distance of the object from the mirror. Regardless
Yes,
of what
sir.
angle you're viewing the mirror at, the image will always be the same distance away from the mirror as the object. So it doesn't matter the distance or the observer or the angle of the observer. So whether you're close to the mirror or further away, it doesn't change how far the image is in the mirror or the plane of the mirror. 42. Which of the following diagram is a graphical representation of current versus potential difference for a metallic conductor at a constant temperature? Answer is A, B, C, or D.
Sir, which number, sir? Sorry.
That is going to be 42. Which one is the correct graph of voltage against current?
D.
Sir, B, sir.
I said not to
Dog.
flex, but watch it.
You said D as in dog? That is
No,
correct.
sir. Oh.
Dog is correct. This, I don't know what that is. This is in the wrong direction.
Sir, what would it be?
I have no idea what B is. I was going to say that it was going to be a semiconductor diode, but that's wrong. This is this part, right? It's wrong for a semiconductor diode, but a semiconductor diode is more like this. This is, I think, a filament lamp right here, but it's supposed to include this part as well. This definitely wrong direction. No idea what this is. But these answer. When a polyethylene rod is rubbed with a cloth, it becomes
Negatively charged by gaining electron.
Yep, that is correct. Which of the following relationships between electrical quantities are correct? V is equal to Pi, R is equal to Vi, Q is equal to IT, and
Yes, sir.
E is equal to VI. You say
Q
Q,
is
you say
equal
C,
to IT.
that's current charge is equal to current times time. This equation here is wrong because V and P should be on opposite sides of the equation. Same thing with this right here. V and R opposite sides of the equation. And I think that's V and I, that should be power, not energy. P equal to IV, yep. It should be power, not energy. You see, is anything that's correct. 45, which are the following circuits where the ammeter reads 0.4 amps and the voltmeter reads 0.6 volts. What is the resistance of R? What's the resistance of R in this simple circuit?
So would it be D?
B is correct. V is equal to IR. Remember, you always take voltmeter readings in parallel and ammeter readings in series. Right, ammeter is 0.4, voltmeter is 0.6. Therefore, the resistor is 1.5 ohms. 1.5 ohms multiplied by 0.4 amps is going to give you 0.6 volts. Right. 46. Two light aluminum spheres A and B are suspended by insulating threads. If they come to rest as shown in the diagram, the force keeping them apart is A, magnetic, B, centripetal, C, electrostatic, and D, gravitational. Which is it?
Sir, will it be electrostatic?
Electrostatic is correct. We did 47, we did 48, we did 49, question 50. This is following shows an AC generator. The part labeled as X in the diagram is known as
Sir, C, sir?
Yep, C is correct. Commuters are in DC motors and they're also known as split rings. So C is the correct answer. All right. Which of the following circuit diagram best represents a series arrangement?
Sir, B, sir.
B.
B as in boy is correct. 52 refers to the following diagram, which represents a straight wire carrying a current into the plane of the paper. Which of the following diagram best represents a magnetic field around the wire? Is it A, B, C, or D?
C.
Sir, may I guess C, yeah. I guess.
You guessing C? All right.
Yes, sir.
Yes, sir.
Anyone for A, B, or D? Correct answer is D, for dog. All right, you have to remember the right hand grip rule, guys. The thumb is the direction of the current, and your fingers show you the direction of the magnetic field, right? Because it's going into the plane of the paper, your thumb should be pointing away from you. And then if you notice your fingers, they're going in a clockwise direction. So it's going to be D for dog. If it was coming out of the plane of the paper, then the diagram would be C, with the exception that this X is now a dot. So if the X was a dot, C would be correct. Because it's an X, the answer is D for dog. Did this already? Did that? Right. 55. In the diagram above, element F has 9 protons. How many protons does element B have? What's the
5.
answer? 5 is correct. Remember, adjacent elements, well, in a periodic table, elements are listed in order of increasing proton numbers. So if this has 9, this must have 5. Just count up 5, 6, 7, 8, 9, or you count down 9, 8, 7, 6, 5. Question 56. The number of neutrons in the nucleus of the nuclide, I think that's radon, 22286 is the number of neutrons. Number of neutrons is
Sir,
C.
136.
136 is correct. But this kind of question, you didn't even need to work it out. We know that it can't be A.
Oh, yeah, sir.
Because that's large up.
Evans.
So it can't be A. It can't be B because that's the mass number, and mass number is number of protons and neutrons. Can't be D because this is the proton number, so it had to be C. Right. Which of the following cannot be deflected by a magnetic field? Alpha particles, beta particles, gamma rays, or electrons?
Gamma.
Gamma is correct. 58. Sodium 24 decays into magnesium 24 with the emission of a beta particle and can be represented by the following equation. Which are the following options should be placed in the box to complete the equation?
Sir, B, sir.
B, that's what you say?
Sir,
Yeah.
boy, sir.
Right? You're correct. B is correct. It's going to be a beta emission. Remember, you have to balance everything. So number of protons must be balanced, as well as the number of, well, the mass number you need to balance it, and the proton number you need to balance it as well. '59, which of the following scientists discovered radium? Marie Curie,
Marie
Isaac
Curie.
Newton.
Marie Curie.
A, sir. Yeah.
One name.
That is correct.
I ignore me.
That is correct. And then question 60. A radioactive isotope has a half-life of 20 days. How many days will it take for a given sample to have its activity reduced to 1/8 of its initial value?
You can like work that out, sir. All right. I really understand that.
Sir,
I go work that.
60 days.
So you
Right,
can like
60
show
days.
where you get that,
No,
sir.
sir, 80.
80 or 60? Which one?
Sir, one
I'll work
second.
it out eventually.
Half will be 20, and then a quarter will be for, sir, 60 days.
Right, you say 60. All right, for questions like this, you can work it out in a table format or however you want, but as you basically said, right, 0 half-lives, right? And to take 0 days. For example, you say 8 for half-life, and put D for days. 0 half-lives, 0 days. And let's say percentage right here, or mass activity, whatever you wanted to put right there, it's going to be 1. Right? So the first half-life is 1, going to take 20 days. And percentage is going to be half. That's half of 1, so half, right? It's not at 1/8 of its original value, so we have to go again. Second half-life, going to take an additional 20 days. So 20 plus 20, 40. Half of half, a quarter. Right? Third half-life, going to take an additional 60 days. And its percentage or fraction is going to be 1/8 of its original value. That's basically how you work it. Basically how you work this kind of question. All right. So guys, we're basically approaching the end of today's session. Is there anything that you guys want to just quickly explain or just look back at before we go?
Sir, what the H at the top for?
The what?
The H at the top in the thing.
Oh, half-life. So that's a number of half-lives. D would be the number of days or the number of years, depending on the context of the question. And then that's just percentage or fraction. It's however you want to work it out. There's no set formula. I like to lay it out like this. where you can see, I can count the number of half-lives, tell the number of days and not fraction. That's how I like to work it out. Other persons have different ways, but it's not like a standard formula to work it out like that.
Sir,
Yeah.
sir, will there be more classes?
For us, none like this, but if you guys want, I can send a few more questions in the WhatsApp group. But there'd be no more marathon session like this. If you want, there is a video from last year where I did, I think the 2021 and the 20, was it 2019 paper? I think I did for paper one, and another facilitator did the paper one. It's about 7 hours long. You can view that video if you want more session. You can watch that one right there.
All right, yes, sir. Thanks, sir.
Sir, yes, sir, you can send the solutions in the group, sir.
Yeah, man, I'm going to send solutions in the group a little bit later. Well, I said by Monday, you should be able to send that there. I said I have a few more adjustments to make to the slide, and then I can send it to you guys. Right, so you can, if you guys have any additional questions, you can send emails or you can message me in the WhatsApp group, or as I said, or can contact the New Jamaica Foundation to find out if they have any other sessions coming up that you would be available or that you'd be interested in getting or participating in. All right, so we just want to thank you guys again for coming out today. It was a pleasure having you guys. And I want to
Yes,
thank
sir,
you
same,
guys. Yeah,
All right, thanks again, sir.
no problem, guys. I do enjoy rest of your day.
Same to you.
Thanks so much for the session, sir.
No problem.